Welcome, curious minds and sleepy thinkers. You found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to tiptoe into one of the most mysterious questions ever asked. Could there be unseen threads, profound connections linking the deepest parts of space with the deepest recesses of our own ocean? Let's drift through this idea slowly, like a leaf falling gently onto a still pond. But don't worry, we'll take it slow. This isn't a race through complex equations or dry facts. It's more like floating through a galaxy of ideas with a cup of chamomile tea, allowing your mind to gently wander and find peace in the immensity of the unknown. The ocean, a vast, shimmering expanse that cradles our world, hides secrets far beneath its surface. And then there is space, an endless canvas adorned with stars, whispering tales of distant galaxies. At first glance, they seem worlds apart, one liquid, and close the other a vacuum and infinitely far. Yet, if we quiet our minds and listen closely, we might just hear the subtle echoes, the surprising harmonies that bind these two realms together. They are in many ways mirror images reflecting each other's profound mysteries and challenges. Imagine for a moment descending into the ocean's abyssal plains where sunlight dares not tread, and then soaring through the cosmic void where the light of distant suns is but a faint memory. The similarities once noticed begin to weave a captivating tapestry, inviting us into a deeper contemplation of our universe. Let us begin with the sensation of cold, a chill that seeps into the very essence of being far beyond what our everyday lives can comprehend. On a winter's morning, we might shiver and pull our blankets tighter, feeling the bite of the frosty air. But this is a gentle caress compared to the profound cold that permeates both the deepest ocean and the furthest reaches of space. In the abyssal plains of our Earth's oceans, miles below the dancing surface, the water hovers just above freezing. It's a constant biting embrace, a perpetual winter that never yields to spring. Here, warmth is a distant memory, a concept belonging to another world entirely. The very molecules of water seem to slow their frantic dance, settling into a quiet, almost reverent stillness. Imagine wrapping yourself in a blanket of ice, not just on your skin, but deep within your bones, a cold that permeates every fiber of your being. This is the enduring chill of the deep sea. Now lift your gaze and let your mind drift through the vast stretches of interstellar space. Here the temperature plummets to near absolute zero, a chilling whisper of -270 degrees Celsius. It is a stillness so profound, it feels as if time itself might hesitate. Its very flow slowed by the absence of energy. There are no warm currents, no gentle breezes. Only the silent, unyielding vacuum occasionally punctuated by the faintest warmth from a distant star, a warmth that dissipates almost instantly into the boundless void. This cosmic cold is not merely a lack of heat. It is an active force, a vast emptiness that drains energy from everything it touches. It's like the deepest, most ancient silence, a quiet so complete that it absorbs all sound, all vibration, leaving only the profound stillness of the universe. Both realms, in their own unique ways, present a cold that is not just a temperature, but a fundamental characteristic of their very existence, a boundary beyond which our familiar warmth cannot easily pass. And then there is the darkness. A darkness so absolute in the ocean's depths that even the most powerful human-made lights struggle to pierce its veil, revealing only fleeting glimpses of the strange life that calls it home. Imagine descending into a world where the sun has never shone, where the concept of dawn or dusk is utterly meaningless. Here, light is not a given. It is a precious, often bioluminescent flicker, a brief ethereal dance of living organisms. It's a darkness that swallows all a velvety blackness that presses in from every side, inviting us to ponder what might exist beyond the reach of our sight, what wonders might unfold in the unseen. It is a realm where eyes, as we know them, become less relevant, and other senses like the subtle vibrations of water or the faint chemical trails take precedence. This is the ocean's ancient primordial night. Similarly, in the cosmic ocean between the bright islands of galaxies, there are immense, lightless gulfs where only the faintest whispers of ancient light occasionally drift, having traveled for eons across the vast emptiness. These are the voids, the great cosmic deserts where stars are few and far between, and the light from distant suns is but a faint memory, a ghostly echo of brilliance. This darkness is not merely the absence of light. It is the overwhelming presence of nothingness, a canvas so vast that it dwarfs even the brightest nebulae into insignificant specks. It's a darkness that swallows all, a profound emptiness that invites us to ponder what might exist beyond the reach of our sight, what wonders might unfold in the unseen. Both the deep ocean and deep space are realms where light, the very essence of our waking world, becomes a rare and precious commodity, forcing life and perception to adapt in astonishing ways. They are truly worlds of shadow, where the familiar rules of vision are suspended and new forms of sensing and being must emerge. And the pressure, oh, the pressure. In the ocean's crushing embrace, every cubic inch of water exerts an unimaginable force enough to flatten steel to render human flesh into something unrecognizable. Imagine the weight of 1,000 elephants pressing down on a single fingernail, multiplied across your entire body. It's a silent, relentless squeeze, an invisible hand that seeks to compress everything into nothingness, reminding us of our profound fragility. Here, the very air we breathe would become a deadly weapon, its gases dissolving into our blood, then expanding violently if we were to rise too quickly. It's a realm where strength is measured, not in muscle, but in the molecular bonds of materials, in the sheer resilience of structures designed to defy the relentless squeeze. The deep ocean is a master of compression, a silent sculptor of matter. In space, while the pressure is often thought of as a vacuum, the forces at play are equally deadly, though different in nature. Here, it is the absence of pressure that becomes the lethal force. Imagine the air within your lungs, the fluids within your cells suddenly having no external force to push against. They would expand violently, explosively, tearing apart the delicate architecture of your body. It's a silent, invisible explosion from within, a force that seeks to rip everything apart rather than compress it. Beyond the immediate danger of internal expansion, there's the relentless bombardment of cosmic rays, high-energy particles that tear through living tissue, silently damaging DNA. These are the invisible pressures of the void forces that demand an almost impossible resilience, a fundamental reimagining of what it means to survive. Both realms, in their own unique ways, present environments where our familiar protective shell, our very atmosphere, is stripped away, leaving us vulnerable to the raw, unyielding forces of nature. They are places where survival is a testament to extraordinary design, whether biological or technological. Then there's the peculiar dance with gravity. On Earth's surface, gravity is a constant, familiar anchor pulling us down, keeping our feet on solid ground. It's the invisible hand that keeps our coffee in its cup and our chairs firmly beneath us. But venture into the deepest parts of the ocean, and a strange buoyancy takes hold, a sensation of being suspended, of floating effortlessly. It's not true weightlessness, but a profound shift in our normal experience of being grounded. The water supports you, cradles you, making your body feel lighter, almost ethereal. Imagine the feeling of being in a dream, where you can move with a graceful slowness, unburdened by the usual pull. This is the ocean's gentle release, a different kind of embrace that lessens gravity's familiar grip. And in space, of course, the absence of a dominant gravitational pull creates a true weightlessness where astronauts float freely, untethered by the familiar pull of a planet. Here, objects drift unbidden, and every movement becomes a graceful, almost balletic glide. It's a liberation from the constant downward tug, a chance to experience movement in 3 dimensions with an entirely new freedom. Imagine pushing off a wall and drifting across a room, or turning a somersault with effortless ease. This is the cosmic dance, a realm where gravity's familiar rules are suspended, allowing for a profound shift in perception and movement. Imagine the shared wonder, the shared disorientation of explorers in both realms if they could somehow survive being there in the first place. This shared experience of altered gravity, this feeling of being released from the familiar hints at a deeper, more fundamental connection between these seemingly disparate environments. It's as if the universe itself is playing a cosmic trick, offering glimpses of a different kind of existence, a different way of being within its grand design, and perhaps most captivating of all. Both the deepest parts of our ocean and the furthest reaches of space are overflowing with unsolved, tantalizing mysteries. Our oceans, vast and largely unexplored, are filled with life we've never seen before, creatures of the deep that defy imagination, adapted to conditions that seem impossible. Every new dive, every new remotely operated vehicle sent into the abyss brings forth new wonders, new questions about the diversity and resilience of life. Imagine a hidden garden, blooming in perpetual night with flowers that glow and creatures that move like shadows. This is the biological mystery of the deep, a testament to life's incredible tenacity. We wonder, how do they survive? What secrets do their unique adaptations hold? What ancient lineages do they represent? These are not just scientific questions. They are profound philosophical inquiries that touch upon our place in the universe and the very definition of life itself. And who can say what lurks in the unexplored corners of space? Are there other forms of life, perhaps vastly different from our own, waiting to be discovered on distant exoplanets, or even within the icy shells of moons in our own solar system? The very thought ignites a spark of wonder, a longing to know what lies beyond the veil of our current understanding. Imagine a distant world shrouded in mist, where oceans of liquid methane might harbor life forms we can barely conceive. Or a subsurface ocean warmed by a planetary core where microbial communities might thrive in eternal darkness. These are the cosmic mysteries questions that challenge our anthropocentric view of existence. The search for extraterrestrial life is not just about finding another species. It's about understanding the prevalence of life in the universe, about whether our existence is a rare cosmic accident or a common occurrence. Both the deep ocean and deep space hold the potential to redefine our understanding of life itself, pushing the boundaries of what we believe is possible. It was this profound sense of the unknown, perhaps, that initially caught me off guard when I heard that NASA, the very name synonymous with rockets and stars, had turned its attention towards exploring the Hadal zones deep in the ocean. After all, NASA is normally about space, about pushing the boundaries of human presence beyond our blue marble. What were they doing deep under the water and on Earth? It felt like a delightful paradox, a cosmic joke played on our expectations, a sudden shift in focus from the infinite void to the crushing depths. It was as if a great explorer accustomed to scaling the highest peaks suddenly decided to plumb the deepest caves. The initial reaction might be confusion, a questioning of purpose, but upon reflection, it begins to make perfect sense. If the challenges of exploring these extreme environments are so strikingly similar, if the questions they pose about life and adaptation are so deeply intertwined, then perhaps the tools, the technologies, and even the mindset required for their exploration are also deeply connected. It's a beautiful thought, isn't it? That the very agency dedicated to reaching for the stars might find its most profound training grounds, its most insightful laboratories, right here, beneath the waves of our own planet. The skills needed to design a submersible capable of withstanding ocean pressures might, with subtle modifications, be applied to a probe designed to penetrate the icy crust of an alien moon. The algorithms developed to navigate an autonomous rover across the Martian landscape could find new purpose guiding a robotic explorer through the dark, unknown terrain of the ocean floor. It's a recognition that the universe, in its elegant design, often presents similar problems requiring similar solutions regardless of scale or location. This unexpected convergence, this shared frontier, suggests that the universe is far more interconnected than we often imagine. The lessons learned in the crushing depths of the Mariana Trench might one day inform the design of a submersible destined for the subsurface oceans of Europa. The strategies for searching for life in the abyssal plains could very well guide our quest for biosignatures on distant worlds. It's a testament to the elegant simplicity of nature's laws, which often manifest in similar ways across vastly different scales and environments. So, as we embark on this quiet journey, let us hold on to this sense of wonder, this gentle curiosity about the threads that bind the cosmic and the oceanic, the known and the unknown. For in understanding one, we might just unlock the secrets of the other. The universe, it seems, is full of such delightful surprises, waiting for us to notice the patterns, to hear the echoes, and to marvel at the intricate dance of existence. It is a dance of challenge, an adaptation of mystery and discovery played out on both the grandest and most intimate stages of our universe. The very act of exploration, whether it be into the inky blackness of our planet's deepest waters or the boundless expanse of the cosmos, is a journey into humility. We are reminded with every new discovery of how little we truly know and how much more there is to learn. The vastness of the ocean stretching beyond our sight mirrors the immensity of space which extends beyond our comprehension. Both are realms where our senses are overwhelmed, where our familiar rules of engagement no longer apply. It is in these places, at the very edges of our understanding, that true wonder blossoms. We are not just seeking new facts or new data points. We are seeking a deeper connection to the universe, a more profound understanding of the intricate web of life and matter that surrounds us. And in this gentle quest, we find not just answers, but also the beauty of the questions themselves. Questions that invite us to dream, to imagine, and to simply be. They are questions that stretch our minds and expand our spirits, pushing us beyond the comfortable confines of the known. The idea that NASA, an organization whose very name evokes images of rockets soaring skyward, would turn its gaze downward into the very heart of our planet's watery embrace, feels like a poetic full circle. It's a recognition that the challenges of extreme environments, whether they be the vacuum of space or the crushing pressure of the deep sea, often demand similar ingenuity, similar technological leaps, and similar human resilience. The training of an astronaut preparing for the isolation and danger of a distant mission finds unexpected parallels in the life of an aquanaut dwelling for weeks in an undersea habitat. Both must learn to manage limited resources to cope with confined spaces and to maintain their focus under immense psychological and physical strain. It's a beautiful testament to the universal nature of exploration, a reminder that the spirit of discovery knows no bounds, whether it's reaching for the farthest star or plumbing the deepest trench. It speaks to a shared human drive, an insatiable curiosity that transcends all boundaries, whether physical or conceptual. And so we begin our quiet descent, not into the cold water itself, but into the warm embrace of understanding. We will explore how our perception of the ocean floor has evolved from a largely unknown abyss to a landscape slowly revealing its contours. We will marvel at the ingenuity of human technology designed to withstand the most hostile conditions imaginable. And we will ponder the profound implications of finding life in places we once thought impossible, both here on Earth and potentially on distant icy moons. This journey is not about finding definitive answers to every question, but rather about appreciating the intricate dance of science and wonder of knowledge and mystery. It's about allowing our minds to float freely unburdened by the need for certainty and simply enjoying the vast, beautiful expanse of what we do not yet know. For in that space of unknowing lies the greatest potential for discovery and the deepest sense of peace. It is a peace found not in knowing all, but in embracing the infinite possibilities that lie just beyond our current grasp. The threads connecting these realms are not always obvious, but they are undeniably there, woven into the very fabric of existence. They remind us that our planet, with its vibrant life and hidden depths, is not separate from the cosmos, but an integral part of it. The same fundamental laws of physics that govern the dance of galaxies also shape the currents of our oceans and the resilience of deep-sea creatures. It is a grand unified narrative, a cosmic poem, written in the language of stars and water pressure and vacuum. And as we listen to its verses, we find ourselves not just learning about the universe, but feeling a deeper connection to it, a sense of belonging in its vast and mysterious embrace. This journey of gentle exploration is an invitation to open our minds to let go of preconceived notions and to allow the wonders of the universe both near and far to wash over us like a calming tide. Tonight we continue our gentle journey into the intertwined mysteries of our deep ocean and the vast expanse of space. Last time we began to sense the whispers of connection between these two seemingly disparate realms, finding shared themes of cold darkness, immense pressure, and profound unknowns. Now let's turn our gaze specifically to the watery heart of our own planet, a place that despite its proximity remains in many ways more alien to us than distant worlds. We will drift slowly through the history of our understanding, or rather, our lack of understanding of the ocean floor, and begin to uncover how even an organization like NASA, born from the ambition to touch the stars, found itself drawn to the depths beneath its feet. Imagine, if you will, standing on the shore of a vast, shimmering ocean. The waves kiss the sand, whispering ancient secrets, and the horizon stretches endlessly, inviting dreams of far-off lands. This surface, ever-changing and beautiful, is what we see, what we experience in our daily lives. But beneath this familiar surface lies a world of unimaginable scale and complexity, a realm largely hidden from our direct view. For centuries, our understanding of what lay at the bottom of these mighty waters was little more than conjecture, a blank canvas upon which sailors and cartographers drew fantastical beasts and imagined abysses. It was a world veiled in a profound watery mystery, a testament to the limitations of our early senses and tools. Consider a time not so long ago, a whisper from the mid-20th century, specifically the year 1957. A scholarly paper published by the esteemed Journal of the Royal Society of Arts made a startling claim, one that might cause a ripple of surprise even today. It stated with quiet authority that the deep oceans covered over 2/3 of the surface of our world. This simple geographical fact was in itself immense. Our blue planet is indeed a watery one, its continents merely islands adrift in a boundless liquid realm. And yet the paper went on to observe something truly profound, that more was known about the shape and surface of the moon, our distant lunar companion, than was known about that of the bottom of the ocean. Pause for a moment and let that thought settle. The moon, a celestial body some 384,400 kilometers away, a silent sentinel in our night sky, held fewer secrets about its topography than the very bedrock beneath the waters that lap at our own shores. This wasn't a casual observation. It was a stark, almost humbling reflection of humanity's priorities and technological limitations at the time. In those days, before the common use of echo-sounding technology, mapping the seafloor was an arduous, often impossible task. Imagine trying to sketch the contours of a vast mountain range while blindfolded, relying only on the occasional uncertain probe. Early explorers might drop a weighted line feeling for the distant thud, but these were mere pinpricks in a gargantuan canvas. The topography, the valleys, the peaks, the vast plains and dramatic chasms of the ocean floor remained largely a ghostly imagined landscape. We knew so little about what truly lay down there, a testament to the immense challenges of peering through such a thick, opaque veil of water. It was a true frontier, not of distant stars, but of our own planet's hidden heart. For centuries, the ocean floor remained largely unmapped, its features a subject of myth and speculation. Explorers returned with tales of the surface of islands and coastlines, but the vast silent world below remained stubbornly out of reach. It was as if we lived on the surface of a magnificent ancient book, yet could only read the cover, the inner chapters sealed away by an impenetrable force. This era, before the advent of technology that could truly see through the water, was defined by educated guesses and speculative drawings of what the deep might hold. It was a time when the very act of charting the ocean depths felt like charting a dreamscape where monstrous creatures and sunken cities could theoretically exist without contradicting any known facts. The ocean, in its immense capacity to hide, became the ultimate realm for our fears and our wildest imaginings, a stark contrast to the burgeoning clarity with which we were beginning to perceive the celestial sphere. However, as the passage of time brought forth ingenuity, we began to chip away at this profound ignorance. We have indeed come a long way since those days of rudimentary soundings and imaginative maps. The tools of our curiosity have grown sharper, our methods more sophisticated. We have sent robotic emissaries into the crushing depths, equipped with eyes and ears far more sensitive than our own. We have developed sonar systems that send out pulses of sound patiently, waiting for the echoes to return, meticulously painting a picture of the terrain below. It is a slow, painstaking process, like trying to assemble a vast jigsaw puzzle with only tiny pieces revealed at a time. Yet, with each echo, with each ping, another small segment of the ocean's hidden face is unveiled, adding to our ever-growing mosaic of understanding. But here is where our gentle journey takes another fascinating turn, revealing the persistence of the unknown. While we have, in a sense, mapped the moon with remarkable precision, thanks to the tireless efforts of satellites orbiting above and powerful telescopes gazing from below our conquest of the lunar landscape, though impressive, is in a different league entirely from our progress with the ocean floor. The moon, in its stark, airless beauty, offers no liquid veil, no impenetrable currents to obscure our view. Satellites can freely sweep across its surface, capturing every crater and ridge in exquisite detail. Telescopes, unimpeded by atmospheric distortions, can resolve features with astonishing clarity. It's a testament to the transparency of space, allowing us to sketch the moon's face with a clarity that feels almost intimate. Yet, as of the time this observation was made, we had still only mapped 23.4% of the ocean floor in high resolution. Let that number settle in your mind like a quiet pebble dropping into a deep well. Less than a quarter of our planet's underwater landscape has been seen with the kind of detail that allows us to truly understand its topography, its hidden wonders. It's a humbling statistic, isn't it? It means that vast, sprawling areas, larger than many continents, remain as mysterious to us as they were to the ancient mariners who first dared to venture beyond the sight of land. It's like owning a magnificent mansion, but having explored only a few of its grand halls, leaving countless rooms and secret passages yet to be discovered. In fairness, and it is important to acknowledge the immense scale we are discussing, this mapped 23.4% still represents an area of over 120 million square kilometers. To put that into perspective, that's about 3 times the surface area of the moon. So the old saying, the one that claimed we knew more about the moon than our own ocean floor, no longer holds entirely true in its starkest form. We have seen a tremendous amount. We have illuminated vast, previously unseen territories. Our maps are certainly richer, our understanding undeniably deeper than in 1957. The progress is undeniable, a testament to human persistence and technological advancement. However, the spirit of that old saying, the underlying sense of a profound gap in our knowledge, still resonates. Hence why, in our modern contemplation, we can instead draw a different comparison, one that perhaps strikes an even deeper chord. Mars, with a surface area of 145 million square kilometers, has been more extensively mapped than the entirety of our ocean floor. Imagine that. We have a clearer, more detailed picture of a cold, distant red planet over 225 million kilometers away than we do of the living, breathing, watery world right beneath our feet. It's a profound gap in our knowledge of our own home, a vast continent of mystery still awaiting its full revelation. This isn't a criticism of our Martian explorations, which are glorious in their own right. Rather, it highlights the immense, almost paradoxical challenge of exploring our own aquatic backyard. It's easier in a sense to look out than to look down to pierce the vacuum of space, than to penetrate the dense, light-absorbing water. This brings us to a crucial point about NASA. The very name, the National Aeronautics and Space Administration, inherently points to the skies, to the atmosphere, and outer space. Indeed, NASA was founded in 1958 with the explicit purpose of expanding human knowledge of phenomena in the atmosphere and in outer space, and developing vehicles and technologies that would help them to do so. Exploring the ocean with its specific pressures, its unique chemistries, its biological complexities was not originally on their radar, or perhaps more aptly on their sonar. Their gaze was fixed firmly upwards towards the cosmos, towards the moonshot and beyond. They were the architects of rockets and satellites, the dreamers of lunar landings and interplanetary voyages. The depths of the Earth's oceans in their initial charter were a distant concern far from their primary cosmic ambitions, yet the threads of connection subtle at first began to emerge. The very act of observing our planet from the vantage point of space, a perspective NASA pioneered, naturally led to a deeper appreciation of Earth as a dynamic, interconnected system. From orbit, the swirling clouds, the vast landmasses, and, of course, the immense blue oceans became visible as components of a single fragile entity. This broader perspective, fostered by their celestial gaze, inevitably drew their attention back to the waters. It was a gradual awakening, a dawning realization that to understand space, to understand our place within the cosmos, one must first profoundly understand our own planet in all its intricate detail. And so quietly, almost imperceptibly at first, NASA began to turn its powerful observational tools towards the watery realm. In 1978, a significant shift occurred, a subtle pivot in their cosmic dance. NASA began monitoring the ocean with their first dedicated oceanographic satellite, CSAT. This wasn't a submersible descending into the deep, but an eye in the sky observing the ocean's surface from above. CSAT was a technological marvel in its own right, capable of collecting a wealth of data that had previously been elusive or impossible to gather on such a global scale. It could measure sea surface winds, painting a picture of the powerful currents of air that sweep across the planet. It could gauge surface temperatures, revealing the subtle thermal gradients that drive oceanic circulation and influence weather patterns. It could assess wave heights, providing crucial insights into the dynamic energy transfer between the atmosphere and the ocean. And it could observe other features, subtle shifts, and patterns that spoke volumes about the ocean's health and its profound influence on our world. This satellite, orbiting far above, became a silent, vigilant guardian of our oceans, a cosmic eye that began to unveil the hidden language of the sea. The data it collected was not merely academic, it was vital. It helped scientists, including those within NASA, to learn more about our planet's oceans and their immense impact on the global climate. Imagine a vast interconnected machine powered by the sun, driven by the turning of the Earth. The oceans are its beating heart, its intricate circulatory system, distributing heat, absorbing carbon, and shaping the very air we breathe. To understand the future of our planet, to predict the subtle shifts and dramatic changes in its climate, we needed to understand the oceans, not just as isolated bodies of water, but as a fundamental driving force in Earth's delicate balance. CSAT marked a quiet but profound expansion of NASA's mission. It was a recognition that Earth itself, with its complex systems, was a planetary laboratory, and its oceans held keys not just to terrestrial climate, but perhaps to understanding other watery worlds in the cosmos. The data gathered from above began to inform theories and models about how planetary systems evolve, how water behaves on a grand scale, and how life might arise and persist in diverse aquatic environments. This initial foray, this gentle dip of a cosmic toe into oceanic waters, was merely a prelude, a quiet overture to some of NASA's most exciting and unexpected engagements with the deep blue. Still, some of NASA's most exciting foray into the ocean only truly began at the turn of the millennium. It was then that the connections, once subtle whispers, became louder, more distinct, revealing a symbiotic relationship between space exploration and deep-sea research. It was discovered that the sea, in its profound and demanding nature, could prepare astronauts for space in ways no terrestrial laboratory ever could. It became a cosmic forge, a liquid crucible in which the human spirit of exploration could be tested and refined. The very challenges that made ocean exploration so daunting also made it an unparalleled training ground for the rigors of venturing beyond Earth. The underlying principle was simple, yet profound: simulated space experiences. If one wishes to prepare for the utterly alien environment of space with its isolation, its confinement, its reliance on life support, then what better place to find a terrestrial analog than the ocean's depths? Both are alien, both demand absolute precision, and both offer no room for error. The cold, the darkness, the pressure or lack thereof in space all combine to create an environment that pushes human endurance and ingenuity to its very limits. It was this shared quality of extreme hostile conditions that began to bridge the seemingly vast gulf between the deep ocean and deep space, transforming a scientific agency's focus from exclusively upward to surprisingly downward. And as we continue our gentle journey, we will explore the remarkable facility that became the nexus of this fascinating convergence. Tonight we continue our quiet descent, not into the cold water itself, but into the warm embrace of understanding how our home planet became an unexpected training ground for those who dream of distant stars. Last time we gently explored the historical mystery of our own ocean floor, a realm less charted than the Moon or Mars, and glimpsed NASA's subtle shift from cosmic observation to terrestrial oceanography. Now let us drift deeper into one of the most remarkable and poetic convergences of deep-sea research and space exploration, the story of the Aquarius Reef Base, a silent, submerged habitat that became a vital cradle for cosmic explorers. Imagine for a moment a place where the air shimmers with a peculiar light, where the only sounds are the gentle hum of machinery and the rhythmic whoosh of life support systems, and where just beyond a thick pane of glass, an alien world teems with life. This isn't a scene from a science fiction film about a distant space station. This is a very real, very tangible place hidden beneath the waves of our own planet. About 8.7 kilometers off Key Largo in Florida lies a jewel of human ingenuity and scientific ambition, the world's only undersea research laboratory, Aquarius Reef Base. Built in 1986, Aquarius is not a sprawling underwater city, but rather a small, intimate habitat, a cozy sentinel against the vastness of the sea. It consists of 3 rooms designed with efficiency and resilience in mind. Though small, it is surprisingly capable, large enough to house 6 people at a push, creating a tight-knit community of aquanauts bound by their shared mission and the unique environment. The heart of the habitat is its main room, a versatile space that combines sleeping and living quarters. Here, bunks are neatly tucked away, transforming into seating during the day, much like the ingenious compact designs seen on spacecraft. It is a place for quiet reflection, for shared meals, and for the necessary human connections that sustain individuals in isolation. Beyond the main chamber, there is an entry dock, a crucial gateway between the pressurized interior of Aquarius and the watery world outside. This is where the aquanauts, often clad in specialized gear, would transition from their dry haven into the surrounding ocean. And connected to this, there's a wet porch for entering the sea around it, an open area perpetually flooded with water, serving as a direct portal to their submerged research site. Imagine stepping out of your front door directly into an alien landscape without the need for complex airlocks, save for the very design of the habitat itself. This ingenious design allowed researchers unprecedented access to the marine environment, offering a unique opportunity to study it in situ without the constant need for surface support. Aquarius was originally conceived with a singular profound purpose to help aquanauts remain at the bottom of the sea for weeks at a time. This seemingly simple goal was achieved through a sophisticated technique known as saturation diving. Normally, when divers descend into the ocean, nitrogen from their breathing gas dissolves into their bloodstream. The deeper they go and the longer they stay, the more nitrogen accumulates. This nitrogen must then be slowly released during ascent through a meticulous process of decompression stops to prevent dangerous conditions, like decompression sickness, often dramatically referred to as the bends. It's like a slowly deflating balloon. If deflated too quickly, it might pop. But saturation diving offers a different path. By remaining at a specific depth, around 19 meters in Aquarius's case, the human body becomes saturated with the gas dissolved in its bloodstream. This means the tissues absorb as much gas as they possibly can for that particular pressure. Once saturated, the clock effectively stops for decompression. This ingenious physiological adaptation allows these researchers to stay at depth without ill effects for much longer periods of time. Instead of being limited to a single dive of just 1 or 2 hours from the surface, a saturation diver from Aquarius could perform a 9-hour dive, day after day, returning to their pressurized habitat at depth and only needing to undergo one long careful decompression at the very end of their multi-week mission. It was a revolutionary approach that unlocked vast new possibilities for sustained undersea research, transforming fleeting glimpses into prolonged, intimate observations. This capability made Aquarius an ideal base for biologists wanting to study the local environment in situ. Imagine being able to observe coral reefs, fish behaviors, and the intricate ecosystems of the deep for extended periods without the constant interruption of ascending, decompressing, and returning to the surface. It was like having a permanent window into a vibrant living laboratory. Scientists could set up long-term experiments, monitor subtle changes, and truly become part of the underwater world they sought to understand. This intimate access allowed for a depth of research that was simply impossible with traditional diving methods, offering unparalleled insights into the delicate balance of marine life. However, the story of Aquarius takes an even more intriguing turn in 2001. It was in this year that NASA's, along with other space agencies such as ESA and CSA, looked at this unique undersea habitat and realized something profound. It made a great space training location. This realization might seem counterintuitive at first glance. Why would an agency focused on the vacuum of space be interested in a watery realm? Yet the similarities once identified were striking and compelling. The very constraints and challenges of living deep beneath the sea mirrored those of living far above the Earth in orbit. Consider the cramped living conditions within Aquarius. With 6 people sharing 3 small rooms for weeks on end, personal space becomes a precious commodity. Every movement must be considered, every interaction managed. These conditions mimic those found on the International Space Station ISS, where astronauts live in a similarly confined environment, sharing living quarters, workspaces, and even personal moments in a tightly choreographed dance of coexistence, forcing astronauts to adapt to such close quarters in a terrestrial setting, provided invaluable psychological and social training, preparing them for the unique demands of living and working in isolation with a small crew far from home. Thus, astronauts who spent a week at Aquarius Reef Base would get a vital taster of what life would be like up there, orbiting hundreds of kilometers above the Earth. It wasn't just about the physical space. It was about the psychological adjustments, the constant awareness of being in an isolated, engineered environment where every system is critical for survival. They learned to share, to compromise, to work as a cohesive unit under the constant hum of life support machinery. This experience transcended mere physical training. It was a profound immersion into the mindset required for long-duration spaceflight, a rehearsal for the extraordinary solitude and communal living that defines life on the ISS. Furthermore, Aquarius allowed astronauts to practice performing experiments and generally get used to the expected and unexpected aspects of life in a hostile environment. In both deep-sea habitats and space stations, experiments must be conducted with meticulous precision, often with limited resources and in challenging conditions. A spilled chemical, a malfunctioning piece of equipment, a sudden anomaly. These can have far greater consequences in an isolated extreme environment. Astronauts learn to troubleshoot, to innovate, and to maintain calm under pressure, developing the crucial problem-solving skills that are paramount in space. The sudden appearance of a curious shark outside the viewport or an unexpected equipment failure due to the corrosive seawater provided real-world scenarios that fostered adaptability and quick thinking, preparing them for the myriad surprises that space might hold. It was a living laboratory for resilience, where the unpredictable nature of an alien environment could be experienced and mastered in a relatively safe yet realistic setting. With this newfound understanding of its potential, NASA began the NEMO program, or the NASA Extreme Environment Mission Operations. And that same year, 2001, they began sending their astronauts to the habitat. This wasn't a one-off experiment. It became a formalized integral part of astronaut training. The NEMO missions were designed not just to simulate space conditions, but to test new technologies, evaluate crew behaviors, and refine operational procedures in a high-fidelity, high-stress environment that closely resembled the challenges of space. The missions were carefully planned with specific scientific and operational objectives, pushing the boundaries of what could be achieved in an isolated, extreme environment. Since then, there have been 23 NEMO missions each, a testament to the program's success and importance. These missions have been a remarkable example of international collaboration, merging astronaut crews from a variety of different space agencies. American, European, Canadian, and Japanese astronauts have all taken part forging bonds and practicing seamless teamwork under pressure. This international cooperation is vital for future space exploration, as missions to the Moon and Mars will undoubtedly be multinational endeavors. By training together in the unique crucible of Aquarius, these diverse crews learn to communicate, coordinate, and trust one another implicitly, laying the groundwork for successful joint ventures far from Earth. The duration of these missions varied, but they lasted up to 3 weeks, providing sustained exposure to the isolated and confined conditions. For 3 weeks, these astronauts truly became aquanauts, living and working in their undersea home, their rhythm dictated by mission objectives rather than the rising and setting of the sun. They conducted scientific research, performed simulated spacewalks outside the habitat, and lived a life that was a profound mirror of their future existence in orbit. This extended immersion was critical for developing the psychological resilience and practical skills needed for the long-duration missions that define modern spaceflight. It was a unique opportunity to experience the physical and mental demands of exploration in an alien environment without the astronomical costs and risks of launching into space. Crucially, these missions provided the aquanauts, now doubling as astronauts, the chance to don deep spacesuits, getting a taste for what spacewalks might be like outside of our planet. While performed underwater, the specialized suits, the challenges of mobility, the reliance on tethered breathing systems, and the meticulous choreography required to perform tasks in a fluid environment all closely mimicked the experience of an extravehicular activity EVA in space. Imagine the sensation of donning a bulky pressurized suit, its weight suddenly made manageable by the water's embrace, then stepping out into a vast, silent world suspended between the habitat and the seabed. It was a profound psychological and physical rehearsal. Readying them for the day, humans return to the Moon or go to Mars. These underwater spacewalks refined their spacewalking techniques, their tool handling, and their ability to cope with unexpected challenges in a simulated microgravity environment. They learned to manage their air supply, their buoyancy, and their mental focus, all critical skills for venturing into the true vacuum. However, this was not the only use NASA had for the ocean. As we gently transition to the next layer of our understanding, we discover that the ocean's role extended beyond just preparing human explorers. Perhaps the most significant training was not for NASA's astronauts themselves, but rather for the machines that would one day visit the largest oceans outside of planet Earth. This is where the narrative shifts from human endurance to robotic ingenuity, from the immediate challenges of terrestrial training to the distant dreams of extraterrestrial discovery. The ocean, in its vastness and its extremes, became a proving ground, a cosmic testbed for the sophisticated autonomous vehicles that might one day probe the liquid hearts of alien worlds. Think of it as a cosmic dress rehearsal. Just as actors practice their lines and movements on a familiar stage before the grand performance, so too must our robotic explorers be tested in environments that closely mimic their eventual alien destinations. And for exploring distant icy moons with subsurface oceans, Earth's own deep waters presented an unparalleled opportunity. The same forces that challenge human aquanauts, the crushing pressure, the near-total darkness, the extreme cold, the complex topography, also challenge robotic systems. By deploying and refining these machines in our own oceans, scientists and engineers can uncover design flaws, optimize autonomous navigation, and perfect sensing capabilities, all before committing to the monumental expense and risk of an interplanetary mission. This strategic pivot from using the ocean to prepare humans for space to using it to prepare machines for alien oceans underscores a profound realization within NASA. The universe is full of water not just on Earth, but locked away beneath icy shells on distant moons. If the quest for extraterrestrial life is to be truly successful, it will almost certainly involve exploring these hidden, watery realms. And what better way to do so than to refine the very tools of exploration in the most similar environment we have readily available? The deep ocean in this context transforms from merely a training ground to an actual proxy alien world, offering invaluable insights and challenges that directly inform our extraterrestrial ambitions. The development of robotic systems capable of operating autonomously in such challenging environments is a cornerstone of future space exploration. Human presence in such extreme places, whether the deep ocean or distant subsurface oceans, remains immensely challenging and costly. Therefore, intelligent, resilient robots become our eyes, our hands, and our scientific instruments. The ocean provides the perfect proving ground for their sensors, their propulsion systems, their communication methods, and their ability to make independent decisions in uncharted territory. It's a painstaking process of trial and error, of learning from failures, and of relentlessly pushing the boundaries of what is technologically possible. So, as we prepare to gently consider the exploration of alien oceans, let us carry with us the image of Aquarius Reef Base. It stands not just as an undersea research lab, but as a silent monument to human adaptability and ingenuity, a testament to the unexpected connections that can emerge when we look closely at the challenges and mysteries of our own world. It is a reminder that the path to the stars sometimes begins by diving deep into the waters beneath our feet, where the most profound lessons for cosmic exploration can be found. It is a harmonious blend of the terrestrial and the celestial, a beautiful illustration of how understanding our blue planet can indeed illuminate the vast, dark expanse of the universe beyond. Tonight we continue our quiet and contemplative journey, gently moving beyond the familiar embrace of Earth's deep oceans to ponder the vast, hidden watery realms that lie far beyond our home. Last time we explored the remarkable Aquarius Reef Base, a silent sanctuary beneath the waves that served as an unexpected cradle for cosmic explorers, preparing them for the rigors of space. Now, let us expand our vision, allowing our minds to drift across the gulf of space, to imagine and gently consider the exploration of alien oceans. Worlds shrouded in ice, holding secrets that could redefine our understanding of life itself. Our solar system, it turns out, is a far wetter place than once imagined. While our Earth boasts its magnificent blue oceans on the surface, A true gem visible from afar, the cosmos holds its own surprising reservoirs. It is home to many large oceans outside of Earth. Vast bodies of water hidden beneath layers of ice, shielded from the harsh radiation and chilling vacuum of space. These aren't just small isolated pockets of ice, but immense globe-spanning seas locked away in an eternal winter. Imagine, if you will, distant planets and moons outwardly appearing as barren frozen spheres, yet harboring warm liquid hearts. Among these celestial water worlds, two stand out as particularly captivating, almost beckoning to us with their icy whispers: Jupiter's moon Europa and Saturn's moon Enceladus. To name just two, these distant siblings in our cosmic family have significant bodies of water beneath their kilometer-thick icy surfaces. Picture a vast frozen sphere, like a gigantic cosmic snowball. But beneath that pristine, unyielding shell lies a churning liquid ocean perhaps as dynamic and mysterious as our own. These moons are not just cold, barren rocks. They are complex, layered worlds with a surprising warmth emanating from within. A warmth that hints at the possibility of life. Consider Europa especially. It is a world of intriguing paradoxes. In spite of only being 1/4 of the Earth's diameter, a mere speck compared to our grand blue marble, scientists believe that Europa holds a staggering secret. This small icy moon is thought to hold twice as much water as all of our oceans combined. Let that incredible fact gently settle into your mind. Imagine gathering every drop of water from every ocean, every sea, every lake, every river on Earth, and then doubling that immense volume. That's the sheer scale of the watery treasure hidden beneath Europa's frozen crust. It transforms this seemingly desolate moon into one of the most compelling targets in our search for extraterrestrial life, a veritable water giant, masquerading as an ice dwarf. This immense volume of hidden water is not merely a scientific curiosity. It is an intriguing concept that fuels our deepest hopes. For even though no sunlight penetrates down to those depths, the very presence of liquid water, especially in a specific configuration, creates a tantalizing possibility. The crucial element here is the mixture of liquid water bordering a rocky inner crust. Imagine our own Earth's oceans, where the water constantly interacts with the seafloor, with its volcanic vents, its mineral-rich rocks, and its dynamic geological processes. This interaction provides chemical energy, a subtle but constant infusion of ingredients that can fuel life even in the absence of sunlight. On Europa and Enceladus, this border between water and rock could provide the very sustenance needed for life to emerge and thrive. The rocky core, potentially warmed by tidal forces from their gigantic gas giant parents, could host hydrothermal vents, much like those found on Earth's own ocean floor. These vents in our own world are oases of life in the perpetual darkness, supporting thriving ecosystems entirely independent of the sun's energy. If such processes occur on these distant moons, then both of these locations would be ideal candidates for life, perhaps not as we know it on the surface of Earth, but life nonetheless. It's a humbling thought that the conditions for life might be far more common and far more diverse than our Earth-centric view has perhaps allowed us to imagine. The universe might be teeming with it in the most unexpected places, with such profound possibilities shimmering on the distant horizon. Scientists have considered how to best test to see if life really has arisen in the oceans of icy moons. It's not a simple task. We cannot simply send a diver or even a traditional submarine to these far-off worlds. The distances are immense, the environments are hostile, and the icy shells are formidable barriers. It requires ingenuity, patience, and a long-term vision. The path to discovery often begins with careful observation from afar, gradually moving closer, gathering more detailed information, much like slowly zooming in on a blurry photograph until the image finally comes into sharp focus. And so the first major step in this cosmic quest is already set in motion. In 2024, NASA will launch the Europa Clipper, a spacecraft designed not to land, but to dance. Its mission is to fly by the moon Europa again and again, making repeated close approaches like a curious hummingbird flitting around a strange flower. With each pass, it will use a suite of sophisticated instruments to scan it, to learn more about the depth of its icy shell. Is the ice thick or thin in certain areas? Are there hidden cracks or plumes that hint at direct connections to the subsurface ocean? These are vital questions for future exploration. Beyond just the shell, Europa Clipper will also strive to determine the composition of its oceans. What chemicals are present in the water? Are there signs of organic molecules, the building blocks of life? Are there salts, minerals, or other compounds that could indicate geological activity at the seafloor? These spectral analyses gathered from afar will be like taking a subtle chemical fingerprint of Europa's hidden sea, offering tantalizing clues about its potential to harbor life. The goal is to generally get a better picture of the moon as a whole, from its icy exterior to its potentially vibrant interior, piecing together the puzzle one flyby at a time. It's a reconnaissance mission, a gentle knock on the door of a distant, mysterious world, patiently waiting for a whisper of a reply. However, Europa Clipper, for all its groundbreaking capabilities, will only be laying the groundwork for future missions. It is the scout, the pathfinder, gathering essential information that will guide the next bolder steps. Its data will help us choose the most promising locations, understand the greatest challenges, and design the most effective tools for a direct encounter. The ultimate dream, the tantalizing goal that gleams on the horizon, is a mission that one day might see cryobots melting through the 10-kilometer thick icy shell of Europa. Imagine a specialized robot, a silent, determined explorer, descending into the heart of an alien world, not by drilling, but by gently melting its way through the solid ice. These visionary cryobots would be equipped with advanced technology, perhaps using nuclear-powered radiators to penetrate its oceans. This would be a slow, painstaking process, a deliberate journey through kilometers of solid ice warmed by a silent internal glow. As the ice melts around them, the cryobots would sink deeper, leaving a trail of melted water behind a watery tunnel, connecting the surface to the hidden sea. It's a concept that sounds like science fiction, yet the fundamental principles are being rigorously explored and tested today. The sheer engineering feat required for such a journey is immense, a testament to humanity's relentless drive to explore and understand. Once these cryobots are down there, immersed in the dark alien waters, a new set of challenges arises. No radio signal will be able to reach them easily. Just as radio waves struggle to penetrate even shallow depths of Earth's oceans, the immense body of water on Europa would effectively silence any direct wireless communication with the surface. It would be like trying to shout across a continent from the bottom of a well. This isolation demands a revolutionary approach to communication and autonomy, forcing our machines to think and act more independently than ever before. Messages will need to be relayed via a vast cable brought down through the ice, along with a cryobot. Imagine a thin, yet incredibly strong and resilient umbilical cord, stretching for kilometers, trailing behind the descending robot. This cable would be the cryobot's lifeline, its sole connection to the surface and to the human minds guiding its mission. It would transmit vital data, images of the alien seafloor, readings of the water's composition, whispers of potential life, back to the surface, and receive commands in return. This engineering solution, while seemingly simple, presents immense challenges in terms of strength, flexibility, and the ability to withstand the harsh conditions within the melting ice tunnel. This reliance on a physical tether means that such cryobots will need to be able to autonomously descend a further 100 to 200 kilometers to explore the dark, chilling, and highly pressurized environment they're likely to find. Once through the ice, they enter a liquid world of profound darkness and immense pressure, a realm where human hands cannot easily guide them. These robots must be capable of making independent decisions, navigating unfamiliar terrain, identifying targets of interest, and collecting data, all without real-time human intervention. They will be our eyes and ears in a world utterly alien, acting as silent, solitary scouts in the cosmic deep. The degree of autonomy required is truly groundbreaking, pushing the boundaries of artificial intelligence and robotic exploration. The ultimate aim of these audacious missions is, of course, to see firsthand what lies below, to search for what alien life might swim in those waters. This is the prize that beckons across the vast gulf of space and ice. Will we find microbial mats clinging to hydrothermal vents, much like those found on Earth? Will there be more complex, perhaps even macroscopic life forms that have evolved in perpetual darkness, feeding on chemical energy rather than sunlight? The possibilities are endless, and the implications for our understanding of life in the universe are profound. To discover a second genesis of life entirely independent of Earth's would fundamentally change our perception of our place in the cosmos. It would transform life from a potentially rare anomaly into a common cosmic phenomenon. So with a mission objective on the horizon to explore deep dark waters in search of never-before-seen life, what better place to start than the unexplored oceans we already have at home? This brings us full circle back to our own planet, where the extreme conditions of the deep sea provide an invaluable proving ground for the technologies and methodologies we will one day deploy on distant worlds. The wisdom, the humility, and the ingenuity gained from exploring Earth's Hadal zones will directly inform our quest for life on Europa and Enceladus. It's a pragmatic yet poetic approach to cosmic exploration, recognizing that the most profound insights often lie in unexpected parallels, and that preparing for the alien often means understanding the extremes of the familiar. Let us consider the depths of Earth's oceans. The deepest parts, such as the Mariana Trench, are only 11 kilometers deep. This might seem shallow compared to Europa's estimated 100-kilometer deep ocean. However, here's where the comparison becomes truly fascinating and relevant for our cosmic ambitions. Due to the gravitational differences between Europa and Earth, the pressure you'd experience between the two are much more comparable than you might think. Europa, being a much smaller world, has less gravity to pull down on its immense ocean. This means that for a given depth, the increase in pressure is less dramatic than on Earth. Europa's 100-kilometer deep ocean is thought to have a hydrostatic pressure between 130 to 260 megapascals. Now, if we were to translate that pressure to an ocean on Earth, it would equate to a depth of around 13 to 26 kilometers. This is a remarkable revelation. It means that the engineering challenges of building a submersible to withstand Europa's pressure are not wildly beyond what we already face for Earth's deepest trenches. It's much better than if you'd had to go hundreds of kilometers down on Earth, which would push material science and engineering to its breaking point. But even with this comparable pressure, it's still no picnic. The pressures are immense, capable of crushing almost any conventional structure, demanding specialized materials and designs. To truly grasp the scale of this challenge, consider the pressure at the bottom of the Mariana Trench, the deepest place in our ocean. It is 100 times the pressure on the surface, an unimaginable force that feels like being under the weight of 100 jumbo jets. This pressure is enough to crush the individual cells in the human body, or to implode most submarines. It is a realm of absolute compression, where weaknesses are ruthlessly exposed. And yet, this is where the mystery deepens, and our hope for alien life strengthens. For in defiance of these crushing forces, life survives there. And it doesn't just survive, it thrives. This is perhaps the most profound lesson Earth's deep oceans can teach us about the cosmos. The resilience of life in such conditions is nothing short of miraculous. The deep-sea explorers of the Galapagos hydrothermal expedition in 1977, venturing into this alien world using a specially reinforced, remotely operated vehicle that could survive those pressures, were met with a sight that defied all expectations. They were shocked to discover not a barren wasteland, but thriving ecosystems gathered around hydrothermal vents on the ocean floor down there. Prior to this, the prevailing scientific belief was that life in the deep ocean would be sparse, perhaps limited to scattered slow-moving scavengers, barely clinging to existence. But what they found was a vibrant, bustling metropolis of life. Tubeworms, crabs, and fish were found in rich abundance, forming dense communities around these vents, which spewed superheated mineral-rich water from Earth's interior. These were ecosystems that did not rely on sunlight for energy, but on chemosynthesis, harnessing chemical reactions from the vent fluids. It was a revolutionary discovery, fundamentally changing our understanding of where and how life could exist. As scientists performed more dives, they found all manner of strange life forms down there. Imagine shrimp-like amphipods, the size of your hand, scuttling across the rocks, their bodies adapted to the immense pressure. Or giant ethereal bigfin squid, their long slender arms trailing behind them, appearing like ghosts in the inky blackness. And even larger squid that were 8 meters long and looked positively alien, their forms so unlike anything we know from the sunlit surface. These incredible creatures inhabit the depths between 6,000 and 11,000 meters in an area known as the Hadal Zone, named after the god of the underworld Hades. Here, life had learned to adapt to conditions in ways no one could have imagined possible. Their bodies are soft and gelatinous, allowing the pressure to pass through them rather than crushing them. Their metabolisms are slow, conserving energy in a resource-scarce environment. And their sensory organs are exquisitely tuned to the subtle cues of darkness, pressure changes, faint chemical trails, bioluminescent flashes. This incredible adaptability gives scientists a better understanding of what might be possible on other worlds that might also harbor vast, dark, high-pressure oceans. It tells us that life, when given even the faintest opportunity, is astonishingly tenacious and endlessly creative in finding a way to thrive. The Hadal Zone is not just a deep-sea trench. It's a living laboratory of extreme biology, offering tantalizing clues to the potential for life across the cosmos. Tonight, our gentle expedition takes us deeper into the heart of Earth's most extreme environments, the very places that mirror the alien worlds we dream of exploring. Last time we marveled at the sheer resilience of life in the Mariana Trench, a testament to nature's boundless creativity under crushing pressures. Now we will consider the unique geography of these Hadal zones, those deep, dark chasms, and discover how NASA, ever pushing the boundaries, plans to use these terrestrial, alien landscapes as a proving ground for the machines that will one day search for life in the hidden oceans of distant moons. The deepest parts of the ocean, those silent, unlit valleys that carve through the seafloor, are not scattered randomly across our watery planet. Instead, they are mostly found near the fault lines of continental plates, those mighty seams where Earth's colossal tectonic plates grind and shift against each other. It's here where one plate, often denser and older, subducts under another, gracefully diving beneath its companion, that these profound abysses are forged. Imagine two immense, slow-moving continents, one sliding beneath the other, creating a colossal wrinkle, a deep, V-shaped furrow in the fabric of the Earth itself. These are the deep trenches, scars of geological power stretching for thousands of kilometers, silent witnesses to our planet's slow, ponderous dance. This unique V-shaped environment created by the subduction zones acts as a natural funnel, a magnificent trap for the very sustenance of the deep. It channels organic debris from above down into a sludgy pool. Picture a gentle, continuous snowfall of organic matter, dead plankton, decaying marine snow, the occasional carcass of a larger creature drifting silently from the sunlit surface world through the twilight zone, and finally settling into these profound troughs. It's a slow, steady rain of life falling into the waiting arms of the Hadal communities below. These trenches become vast, nutrient-rich reservoirs, accumulating food in a world where sustenance is otherwise scarce and precious. And within this vast, dark larder, life has developed an astonishing efficiency. Whenever a carcass falls down, there perhaps a whale or a large fish that succumbed to age or injury near the surface The organisms in the Hadal Zone, those hardy residents of the deep, are somehow able to quickly detect it and arrive within minutes. It's as if a silent alarm bell rings through the water, a subtle chemical whisper carried by the currents guiding these specialized scavengers to their unexpected feast. Imagine a banquet table appearing instantly in the middle of a desert. Such is the impact of a falling carcass in these nutrient-limited depths. These creatures, with their exquisitely tuned senses, are masters of resource utilization, transforming fleeting opportunities into the energy needed to survive and thrive in a world of perpetual scarcity. Their rapid response is a marvel of adaptation, demonstrating an ecological efficiency almost unimaginable in our more abundant surface world. Beyond these rare bountiful feasts, other organisms rely on nutrient-rich liquids pumped out of thermal vents. These are the true oases of the deep, the vibrant, superheated springs bubbling from the Earth's interior, often found along the very fault lines that create the trenches. These vents spew forth a chemical cocktail of dissolved minerals, hydrogen sulfide, and other compounds, providing the raw ingredients for chemosynthesis, a process where microbes convert chemical energy into organic matter, forming the base of an entirely independent food web. Here, life flourishes without a single ray of sunlight, drawing its energy from the very heart of the Earth. It's a profound demonstration of life's adaptability, its ability to find sustenance in the most unexpected and challenging forms, showing us a potential blueprint for life on other worlds. If you were to gather all these trenches, these profound scars on our planet's face, and unite them into one continuous landmass, you would end up with an area of astonishing scale, a single vast territory the size of Australia. Imagine that. An entire continent, hidden beneath the waves, largely unexplored, teeming with unique life forms and geological wonders. It is, in essence, a whole unexplored continent right here on Earth, a testament to the immense unknowns that still reside within our own blue marble. This isn't just a metaphor. It's a call to action, a reminder that the greatest frontiers are not always distant stars, but sometimes the very ground beneath our feet, veiled by the enigmatic embrace of water. This hidden continent holds countless secrets waiting for the tools of human ingenuity to peel back its watery curtain. And it is precisely these enigmatic regions that have captured the imagination and strategic focus of NASA. Their ambition, ever reaching, is now extending downwards. NASA wants to explore these regions using autonomous drones, intelligent, self-guided robots that can navigate the treacherous landscape of the deep without direct human control. Imagine a fleet of silent mechanical scouts equipped with their own decision-making capabilities, gently descending into the abyss. Perhaps even whole swarms of them, a synchronized ballet of exploration, working in concert to map and probe the hidden corners of this underwater continent. These drones would be designed to detect locations of interest such as thermal vents, those shimmering oases of life, using an array of sophisticated sensors. They would be capable of mapping out the terrain using cameras and onboard AI, meticulously charting the ridges and valleys, the plains and peaks of the Hadal Zone, much like an artist slowly sketching a complex landscape. The artificial intelligence guiding these drones would be similar to that used by the Perseverance rover on Mars, a testament to the shared challenges of remote autonomous exploration across seemingly disparate environments. The principles of navigation, obstacle avoidance, and scientific target identification developed for the Martian surface find a surprising second home in the Earth's deep ocean. It is a beautiful example of cross-disciplinary learning, where the tools for space exploration can unlock the secrets of our own planet. However, the task of designing and deploying such drones in the Hadal Zone is not merely challenging. It is truly formidable. Not only would such a drone need to be able to withstand the excessive pressure, a force that could crumple most materials like paper, but it would also need to contend with another equally demanding environmental extreme. The temperatures around those vibrant thermal vents, the very oases of life, can spike to hundreds of degrees Celsius. Imagine transitioning from water barely above freezing to superheated liquid hot enough to melt lead, all within a few meters. These drones would need to be able to survive rapid temperature swings if they are to survive at all, a testament to the extreme demands placed upon their materials and internal systems. It's a test of ultimate resilience, a brutal proving ground for technologies that must one day operate flawlessly in environments equally, if not more, unforgiving. The path to such advanced capabilities is paved with both triumphs and heartbreaking setbacks. In 2014, one such deep-sea drone, known as Nereus, was sent into the Kermadec Trench off the coast of New Zealand. This particular trench, with its challenging depths and dynamic environment, had been the area NASA had selected as testing ground for its new equipment. Nereus was a marvel of engineering, a remotely operated vehicle capable of diving to the deepest parts of the ocean. It had successfully completed dives in other Hadal zones before bringing back invaluable data and images from worlds unseen. There was great hope for its mission in the Kermadec Trench. However, sadly, Nereus was not able to survive the pressure down there on this particular dive, in spite of having succeeded on Hadal dives before. In a tragic and sudden event, it imploded. The immense pressure and invisible relentless force found a weak point, and the advanced machine was instantly crushed. It was a stark and somber reminder of the unforgiving nature of the deep, a poignant illustration of the fine line between triumph and failure in extreme environments. Later pieces of plastic were found floating to the surface, the fragmented remnants of a noble attempt to push the boundaries of exploration. It was a somber lesson, a testament to the immense engineering challenges that remain, but also a catalyst for renewed efforts and even more robust designs. But the spirit of exploration, like the ocean currents themselves, is relentless. Failure in the world of scientific discovery is often merely a stepping stone, a profound lesson that illuminates the path forward. And so, NASA's latest drone is Nereus's descendant, a new generation born from lessons learned and ambitions undimmed. This successor is a smaller, lighter autonomous submarine known as Orpheus. Its name, echoing the mythical Greek poet who ventured into the underworld, feels particularly apt for a machine destined for the abyssal depths. The design philosophy behind Orpheus marks a deliberate shift: lighter materials, more streamlined forms, and an even greater emphasis on autonomy, reducing reliance on human intervention in real time. Orpheus, in its cautious yet determined development, has yet to enter the depths of the Hadal Zone. Instead, it is being put through its paces in shallower waters, meticulously tested and refined in less punishing environments, much like a young bird learning to fly in a sheltered nest before venturing into the vast sky. This careful, iterative approach is essential for ensuring its resilience and reliability. Every system, every sensor, every line of code is rigorously examined, preparing it for the ultimate test. It's a testament to the scientific method where patience and precision pave the way for monumental achievements. But if it works, if Orpheus proves its mettle in the demanding conditions of Earth's deep sea, its potential reach extends far beyond our home planet. Its lighter design would make it easier to transport on a rocket to the oceans of Europa at some point in the distant future. Imagine this sleek, autonomous explorer, having proven its capability in Earth's darkest waters, nestled within the payload bay of a powerful rocket, destined for a journey of hundreds of millions of kilometers. The lessons learned, the technologies perfected, and the confidence gained in Earth's Hadal Zone would be directly transferable, enabling humanity's boldest dreams of exploring extraterrestrial oceans. It is a technological lineage, a direct link between the depths of our own world and the possibility of life on a distant moon. This dream of sending Earth-forged explorers into alien seas might not be so distant after all. The pace of scientific and technological advancement often outstrips our imagination. In 2023, NASA's Planetary Exploration Science Technology Office gathered a team of 40 top researchers from multiple fields in the California Institute of Technology to engage in a profound and exhilarating discussion how close we might be to making this trip. These were not casual conversations, but rigorous scientific and engineering assessments, bringing together the brightest minds in planetary science, robotics, and deep-sea exploration. The atmosphere must have been electric with the potential of such a mission. Their findings were both surprising and immensely encouraging. A surprising amount of technology needed is already there. This revelation speaks volumes about the synergistic nature of scientific progress, where breakthroughs in one field inadvertently pave the way for achievements in others. The sensors developed for Earth-observing satellites, the autonomous navigation systems for Martian rovers, the robust materials engineered for deep-sea submersibles. All these disparate pieces are beginning to fit together, forming a coherent blueprint for a future mission to an ocean world. It's like finding that all the different threads you've been weaving in separate projects suddenly come together to form a magnificent tapestry. Their conclusion was a whisper of profound hope that the mission was feasible, scientifically compelling, and the most plausible near-term way to directly search for alien life in situ on an ocean world. This wasn't just a hopeful wish. It was a carefully considered scientific assessment, suggesting that the dream of probing alien oceans is moving from the realm of pure science fiction into the tangible domain of achievable scientific missions. The scientific compellingness lies in the immense implications of finding a second genesis of life, while the feasibility highlights the growing maturity of the necessary technologies. It is a thrilling prospect, a horizon that seems to draw ever closer. With the combined information being gathered by Europa Clipper, patiently orbiting and scanning from afar, and the technical experimentation being done with Orpheus and other autonomous submarines like it, we are steadily building the knowledge and the tools necessary for this monumental undertaking. Europa Clipper is our distant eye-gathering intelligence about the icy shell and the ocean's chemistry. Orpheus and its brethren are our terrestrial apprentices learning the art of deep-sea survival and autonomous exploration. Together they form a powerful duality pushing the boundaries of what is known and what is possible. Perhaps it is something we will see within our lifetimes, although no concrete plans have been made yet. The future, like the deep ocean, remains a realm of possibilities, sometimes shifting, sometimes revealing itself in unexpected ways. But the momentum is building. The technology is advancing, and the scientific drive to answer one of humanity's most profound questions, are we alone?, is stronger than ever. It's a gentle anticipation, a quiet hope that one day we will witness the culmination of centuries of curiosity, the moment when our Earth-born machines dip into the alien waters of a distant world. When it finally does happen, though, and a human-made drone starts to swim in those dark seas across the gulf of space, what will it see? Will it be utterly alien beyond our wildest dreams? Or perhaps in a profound and humbling way, it will feel strangely like home. This final thought for our chapter invites a deeply meditative reflection on our place in the universe and the fundamental nature of life itself. We are, after all, water-based life forms here on Earth. Our very existence, from the smallest cell to the largest creature, is intrinsically linked to this remarkable liquid. The first large complex animals formed in our oceans, a testament to water's role as the cradle of life on our planet. It was in that primordial soup in those ancient seas that the complex dance of evolution began, slowly giving rise to the incredible biodiversity we see today. And even now, after billions of years of evolution, all life is dependent on water to live. It is the universal solvent, the medium for all biochemical reactions, the silent essential element that makes existence possible. Without water, our planet would be a barren, lifeless rock. So rather than encountering arid, rocky, and dusty wildernesses as we often imagine distant planets, there will be something strangely soothing about exploring oceans beyond our own, like entering a place we already know, even though we've never been there before. Imagine plunging into a cosmic sea and finding echoes of Earth whispers of familiarity in the alien currents. It's a comforting thought, suggesting a deeper underlying commonality in the universe, a shared blueprint for life that transcends the vast distances and different celestial addresses. It speaks to a profound connection, a cosmic kinship, reminding us that water, the very essence of our being, might also be the key to understanding life far beyond our blue world. Tonight we continue our quiet and contemplative journey, gently moving beyond the fascinating parallels between Earth's deep oceans and the hidden seas of distant moons. We've touched upon the incredible resilience of life and the ingenuity of human technology, always striving to reach into the unknown. Now let us bring these threads together and softly gaze towards the horizon of discovery, pondering not just the how of finding life beyond Earth, but the profound what if. What if we are not alone? And what implications would such a discovery hold for our understanding of life itself? The very notion of exploring alien oceans, once relegated to the realm of speculative fiction, is now shimmering on the cusp of reality. The commitment to this grand endeavor is not merely a flight of fancy, but a culmination of decades of scientific inquiry and technological advancement. In the pivotal year of 2023, NASA's Planetary Exploration Science Technology Office orchestrated a gathering of minds that truly embodies the spirit of our gentle exploration. They brought together a formidable team of 40 top researchers from multiple fields in the California Institute of Technology. Imagine the quiet hum of brilliant minds drawn from diverse disciplines: astrobiology, oceanography, robotics, material science, and planetary geology, all converging with a singular thrilling purpose to discuss how close we might be to making this trip. It was a testament to the integrated nature of modern science, where the most profound questions require a symphony of expertise. The discussions were not mere theoretical musings. They were rigorous assessments, peeling back the layers of the complex challenge, examining every facet of a potential mission. And what emerged from these deep dives into feasibility was truly remarkable. There was a surprising amount of technology needed already there. This revelation speaks volumes about the incremental yet relentless march of human ingenuity. Innovations born from the necessity of deep-sea exploration on Earth, or the demanding precision of Martian rovers, or the sophisticated sensors developed for orbiting telescopes, are now finding unexpected synergy. It's as if various streams of scientific and engineering progress, flowing independently for years, are now beginning to converge into a mighty river capable of carrying us to distant watery worlds. The necessary components, from advanced power sources to resilient communication systems, from autonomous navigation software to miniaturized scientific instruments, are maturing at a pace that inspires quiet optimism. The conclusion of this esteemed gathering was not merely positive. It was a whisper of profound hope, a clear affirmation of a bold new chapter in exploration. They found that the mission was feasible, scientifically compelling, and the most plausible near-term way to directly search for alien life in situ on an ocean world. Feasible suggests that the challenges, though immense, are within our current or soon-to-be-acquired technological grasp. Scientifically compelling speaks to the immense implications of such a discovery, a prize that would reshape our understanding of life's place in the universe. And most plausible near-term way tells us that among all the grand visions of finding extraterrestrial life, this journey to an ocean moon represents our clearest, most direct path forward in the foreseeable future. It's a powerful endorsement painting a picture of a future that is not just a dream, but a tangible, achievable quest. This growing confidence is deeply rooted in the combined information being gathered by Europa Clipper and the technical experimentation being done with Orpheus and other autonomous submarines like it. Europa Clipper. Our silent sentinel is diligently collecting precious data from afar, meticulously scanning the icy shell of Europa, probing its composition and giving us vital clues about its hidden ocean. It's like a patient detective gathering subtle evidence, piecing together the puzzle from every angle. Meanwhile, Orpheus, the resilient descendant of Nereus and its brethren, are rigorously testing the very tools of direct exploration in the demanding yet familiar crucible of Earth's deep sea. They are proving the concepts, refining the designs, and demonstrating the autonomy required for such an undertaking. Together, these two streams of endeavor, remote sensing and terrestrial prototyping, are building a robust foundation, making the seemingly impossible steadily, gently probable. And so we are left with a quiet, thrilling question that hangs in the air like a distant star. Perhaps it is something we will see within our lifetimes, although no concrete plans have been made yet. The future, like the deep ocean itself, remains a realm of boundless possibilities, sometimes shifting, sometimes revealing itself in unexpected ways, but the momentum is undeniably building. The technology is rapidly advancing, and the scientific drive to answer one of humanity's most profound questions, are we alone, is stronger and more focused than ever before. It's a gentle anticipation, a quiet hope that one day we will witness the culmination of centuries of curiosity, the moment when our Earth-born machines dip into the alien waters of a distant world, carrying with them the dreams and questions of all humanity. The thought alone is enough to stir the imagination, to paint vivid pictures in the quiet theater of the mind. Now let us allow our thoughts to drift to wonder about the moment that will inevitably arrive. When it finally does happen, though, and a human-made drone starts to swim in those dark seas across the gulf of space, what will it see? Will the landscape be utterly alien beyond our wildest dreams, a panorama of bizarre formations and unimaginable creatures? Or perhaps in a profound and humbling way, it will feel strangely like home. This final thought for our chapter invites a deeply meditative reflection on our place in the universe and the fundamental nature of life itself, a concept that weaves through every corner of existence. This sense of potential familiarity is rooted in a fundamental truth about ourselves. We are water-based life forms here on Earth. Our very existence, from the smallest single cell to the grandest whale, is intrinsically linked to this remarkable liquid. Water is not just a backdrop for our lives. It is the very solvent of our being, the medium in which all our biochemical processes unfold. Our bodies, in their intricate design, are primarily water, a testament to its foundational role. It is a cosmic liquid essential for life as we understand it, and its ubiquity across the universe, particularly in icy moons, holds a deep resonance for us. And the history of life on our planet further underscores this profound connection. The first large complex animals formed in our oceans in those ancient, life-giving seas. It was in that primordial soup, in those warm churning waters, that the intricate dance of evolution began slowly giving rise to the incredible biodiversity we see today, from the smallest plankton to the towering redwood trees. The ocean was the original cradle, the fertile ground, where life first blossomed in its magnificent complexity. Even now, after billions of years of evolution, after life has spilled out onto land and soared into the skies, all life is dependent on water to live. It is the universal solvent, the indispensable medium for all biochemical reactions, the silent essential element that makes existence possible. Without water, our planet would be a barren, lifeless rock, a stark reminder of its critical role. So when we envision exploring distant oceans, the thought is not necessarily one of stepping into a completely alien landscape, devoid of all familiarity. Rather than encountering the arid, rocky, and dusty wildernesses that often characterize our perception of other planets like Mars, there will be something strangely soothing about exploring oceans beyond our own. It might feel like entering a place we already know, even though we've never been there before. Imagine plunging into a cosmic sea and finding echoes of Earth whispers of familiarity in the alien currents. Perhaps the subtle dance of light, or the way currents carry nutrients, or the very chemical signatures of life itself will resonate with something deep within our own biological memory, a memory stretching back to the earliest oceans on Earth. It's a comforting thought, suggesting a deeper underlying commonality in the universe, a shared blueprint for life that transcends the vast distances and different celestial addresses. It speaks to a profound connection, a cosmic kinship, reminding us that water, the very essence of our being, might also be the key to understanding life far beyond our blue world. The question then gently arises, almost like a bubble rising from the deep. Does something lurk in those alien seas? Is there a whisper of life, a faint echo of existence hidden beneath those frigid shells? While it's important to acknowledge that it's only speculation at this stage, the sheer possibility that this might be true is enough to ignite a profound sense of wonder. The mere contemplation of it expands our minds, challenging our assumptions about the uniqueness of life on Earth. It opens up a universe of possibilities, transforming the cold, silent void into a vibrant, potentially teeming cosmos. It is a speculation that fuels research, inspires dreams, and propels humanity forward into the unknown. For if we were to discover that life came to exist, not once but twice, in just our own solar system, the implications would be nothing short of revolutionary. This single finding, a second genesis, would have massive implications on life's prevalence in the universe as a whole. It would suggest that the conditions for life are not as rare as we once might have believed, that the spark of existence might ignite more readily than we currently understand. Imagine if finding 2 instances of life in one small planetary neighborhood were to imply that the universe is not a desolate, empty expanse, but rather a vast cosmic garden filled with countless forms of life, blooming in countless different ways. It would mean life is likely abundant, perhaps flourishing in forms we can barely conceive, thriving in environments we once dismissed as uninhabitable. This revelation would transform our perception of cosmic loneliness into one of cosmic companionship, albeit with life forms that might be utterly alien in their appearance and biology. It would imbue every distant star, every shimmering nebula with a new sense of potential, a quiet promise of existence. The universe would suddenly feel richer, more vibrant, more alive. And with that understanding, we ought to be ready to see a lot more of it out there. Our search methods would adapt, our assumptions would shift, and our eyes would be open to the myriad ways life might manifest across the vast tapestry of the cosmos. But proving it is the challenge, the Everest, that still looms before us. The path to definitive answers is long and arduous, requiring painstaking effort and relentless innovation. Only by perfecting the technology here on Earth will we be able to crack open those frozen shells, enter those inky depths, and find the definitive answers we seek. The lessons learned in Earth's Hadal Zones, the advancements made in autonomous robotics, the breakthroughs in sensing technologies. These are the foundational steps. Each successful dive in our own oceans, each piece of data gathered by Europa Clipper, builds towards that monumental moment when a cryobot descends into the hidden sea of an alien moon. It is a patient, determined march towards understanding driven by the profound desire to know, to truly know if we share this cosmic dance. For NASA, the journey to answer one of humanity's deepest questions, their mission to find life in our solar system, begins in our oceans. It is a beautiful full circle, a poetic testament to the interconnectedness of all things. The depths of our blue planet are not just training grounds or proxy alien worlds. They are living laboratories, teaching us invaluable lessons about the tenacity of life and the ingenuity required to find it no matter where it hides. The very act of plumbing Earth's deepest waters is in essence a prelude to reaching for the stars, for the hidden oceans beyond. It is a journey that asks us to look both inward and outward, to embrace the mysteries close at hand and the wonders far away, knowing that in the quiet echoes between them, the most profound truths might be revealed. And as we close this chapter, let us hold on to this sense of vast possibility, allowing the gentle current of these thoughts to carry us deeper into the night. Tonight, our gentle journey takes a turn from the depths of the ocean and the expanse of space, bringing us back to a powerful silent force that shapes our very home ice. Last time we pondered the profound implications of finding life in alien oceans, guided by the lessons from Earth's own abyssal realms. Now let us turn our gaze to the planet's poles, to the vast, shimmering expanses of frozen water, and listen to the ancient stories. They whisper stories of history, of colossal energy, and of a future that is subtly yet profoundly being forged by their gentle melt. Imagine taking a walk with me through an ancient verdant land. The air perhaps is cool and crisp, carrying the scent of damp earth and thriving foliage. So vivid are the colors of the entangled fauna, the deep greens of moss, the vibrant hues of blossoms that it takes your breath away. And the aroma, a rich earthy perfume, fills your senses, telling tales of centuries of growth. It is a world teeming with life, a vibrant tapestry woven by the delicate hand of nature. But then, as you truly allow yourself to settle into this imagined landscape, it takes you an age to notice something isn't as it should be. A subtle disharmony, a quiet absence. It's all quiet. The near absence of birds and mammals is the only indication that this land is slowly, inexorably dying. Its fate, unknown to its flourishing inhabitants, was sealed by the ending of an ice age. A profound shift in the Earth's grand climate dance was underway, and its watery consequences were inevitable. The waters are rising. Gently, imperceptibly at first, then with increasing certainty. The lush landscape below your feet, the very ground you stand upon, which once supported such vibrant life, will soon be 30 meters below the surface of the Pacific. It's a slow quiet, drowning a transformation of land into a watery grave. Any species able to migrate, those with wings or strong limbs, have escaped embarking on desperate journeys to continue their fight for survival in a warming, shrinking world. But those given life by their roots, the ancient trees, the delicate flowers, the countless species inextricably bound to the land beneath them, are held to perish by them. They are the silent witnesses to this profound change, rooted in their fate, unable to flee the encroaching tide. It is a sobering image, a glimpse into a world reshaped by the powerful yet often unseen forces of our planet. What is happening here? What can we learn from the history recorded deep in the melting polar ice? This question holds a profound significance, of vital importance for our present and our future. Because right now it's happening again. The whispers from that ancient verdant land are echoing in our own time, though the causes and complexities are subtly different. The great ice sheets, those colossal frozen libraries of Earth's past, are once again stirring, yielding their ancient secrets and sending their vast meltwaters into the global ocean. So we must ask, what is causing the ice caps to melt in the present? Is it merely a continuation of natural cycles, or something new? Something influenced by our own presence? How will it affect the most powerful climate systems on Earth? How will these vast, slow-moving shifts impact the delicate balance that sustains our modern world? And what hidden dangers does the ice contain? What ancient microbes, what long-dormant chemicals might be reawakened and released as the frozen giants recede? These are not questions to be rushed, but to be contemplated with a quiet, earnest curiosity. I am Alex McCohen, and you're watching Astrum. Join me today as we look at what makes ice such an interesting and crucial feature of our planet, and imagine a future, wetter Earth. One whose existence may have already been forged by the choices we make and the subtle shifts occurring beneath the surface of our awareness. We will explore the surprising power of ice, its role as a planetary buffer, and the intricate dance between heat, water, and atmosphere that defines Earth's delicate climate. On Astrum, we love to explore gigantic objects in our universe, whose scale through time and space stretch almost beyond our grasp. Look up towards Cassiopeia, that graceful W in the night sky, and there is our closest galactic neighbor, Andromeda, a majestic spiral galaxy 2.5 million light-years away, a colossal island of stars 200,000 light-years from edge to edge. Yet despite its staggering magnitude, we can connect to it. We see its light, a gentle echo from a distant past, and we can with our minds conceptualize its immense scale. It feels grand, but somehow comprehensible in its cosmic distance. Yet it is curious to me that looking only 80 years to our future feels too distant to connect with, too abstract to truly grasp. It feels harder somehow to understand that the things we do today affect tomorrow's world, that our present actions cast long shadows into the generations yet to come. The future in its proximity can often feel more remote than the ancient light of distant galaxies. It's a paradox of human perception, where the immediate looms large and the near future feels amorphous. So let me take you there gently, quietly into that future through the lens of what is happening to our planet's ice. At the beginning of our journey into this future, into this understanding, is the ice itself. Ice is a truly remarkable substance, one that holds a hidden power, a silent strength that belies its seemingly fragile appearance. It is a substance that can store vast amounts of energy, far more than we might intuitively realize. Think of it not just as frozen water, but as a colossal battery quietly holding immense power within its crystalline structure. As a comparison, consider the energy stored in our modern world. An electric car, sleek and powerful, capable of accelerating tons of metal to over 160 km/h and carrying both it and you hundreds of kilometers, represents a marvel of energy storage and conversion. Yet the energy stored in such a vehicle could scarcely melt ice that would fit on its back seats. Let that image settle in your mind. A small block of ice, seemingly innocuous, holds more latent thermal energy, more resistance to change than a high-performance electric vehicle. This simple comparison vividly illustrates the immense energy required to transition ice from its solid to its liquid state, a process known as latent heat of fusion. It is this incredible capacity to absorb and release energy that makes ice such a profound player in our planet's climate system. Indeed, the energy storage capacity of ice is a large part of the reason that the climate has been so stable for the past 12,000 years. This period, known as the Holocene epoch, has been a unique and relatively stable era in Earth's long turbulent history. For 12 millennia, the Earth's average temperature has remained within a remarkably narrow band, allowing for the flourishing of human civilizations and the development of agriculture. The ice, in its vast, silent presence at the poles, has been acting as a buffer against extreme temperature rises and falls. Like a giant, slow-acting thermostat, it has absorbed excess heat when the planet warmed slightly, preventing runaway heating, and released heat when temperatures dipped, mitigating extreme cold. This stability, this delicate balance, has been fundamentally underpinned by the mighty ice caps. The Holocene has been a unique period in Earth's history for another reason too: the rise of human civilizations made possible through the development of agriculture. The invention of farming dependent on predictable seasons and stable climates allowed nomadic hunter-gatherer societies to settle, to build villages, and eventually cities. This agricultural revolution, the bedrock of human progress, would have been profoundly challenged, perhaps even impossible, without the climatic stability provided by the vast reserves of polar ice. The ice, in a silent, profound way, has cradled the very development of human society. Now let us turn our attention to these colossal guardians of Earth's climate, the ice caps themselves. The Antarctic ice cap first formed around 37 million years ago, an ancient sentinel witnessing the slow dance of continents and the ebb and flow of ancient seas. The Arctic ice cap formed much later, around 2.7 million years ago, a relative newcomer in geological time, yet still unimaginably old. Its age, in a breathtaking cosmic coincidence, is as old as the light reaching us from Andromeda, the very galaxy we contemplated earlier. Imagine the photons that left Andromeda 2.7 million years ago, embarking on their epic journey across the cosmos, were already in transit when the Arctic ice cap began its formation. It's a profound link between the deep time of Earth and the vast expanse of the universe, and both of these colossal caps are important for our stable climate to this day. Their historical size has largely been defined by Earth's position and tilt in the solar system. subtle orbital wobbles that have profound effects. These movements are known as Milankovitch cycles, which describe the long-term variations in the amount of solar radiation reaching Earth. They account for the great ice ages, the slow rhythmic pulses of glacial advance and retreat over hundreds of thousands of years. These cycles are like a grand cosmic clock, gently dictating the planet's long-term climatic rhythm. According to these cycles, and based on our current position in this cosmic dance, the ice at the poles should be increasing. We should, by the natural rhythm of our planet's orbital mechanics, be heading into an ice age. The sea levels in this natural progression should be falling as the ice caps get deeper, accumulating more and more frozen water. It's a slow, majestic geological process, a natural cooling that has characterized much of Earth's recent history, but instead a profound anomaly. A quiet discord in the symphony of planetary cycles has emerged. The polar ice is melting. Not slowly, not in sync with the natural rhythms, but with a surprising and accelerating pace. Massive amounts of energy are being absorbed by the caps, transforming solid ice into liquid water, a visible testament to a powerful underlying change. And not only are we going in the opposite direction that the Milankovitch cycles predict, the ice loss is accelerating. This acceleration is the quiet alarm bell, the unmistakable sign that something beyond natural variability is at play, pushing our planet's climate system into an uncharted territory. The implications of this accelerated melt are vast, shaping the very coastlines of our future. Should all the ice melt, we are facing a 70-meter sea level rise, an unimaginable deluge that would fundamentally redraw the map of our world. Picture a watery invasion silently claiming vast swathes of land, submerging entire cities. Coastal metropolises, vibrant hubs of human activity, would become underwater ruins. It's a scenario that paints a stark and sobering picture of a transformed Earth. Fortunately, that degree of ice loss is exceptionally unlikely to occur within any time frame relevant to human civilization. The sheer volume of ice, its thermal inertia, and the complex feedback loops within the climate system mean that such a catastrophic, complete melt would take millennia. However, while the most extreme outcome remains a distant nightmare, the reality of significant sea level rise in the coming centuries is a certainty. And so, we do need to know how much sea level rise to expect so that we can plan ahead and protect Earth's ecosystems and our own communities. This is not about alarm, but about sober assessment and thoughtful preparation, understanding the trajectory of change and preparing for its gentle yet powerful consequences. To predict just how much we need to understand why and how the ice is melting. It is here that the human story intertwines most profoundly with the planetary one. We know with growing certainty that the release of greenhouse gases is a driver of today's global warming, overpowering the Milankovitch cycles, pushing our planet's thermostat upwards. These gases, a blanket of invisible molecules, are trapping heat in our atmosphere, fundamentally altering the energy balance that has governed Earth's climate for eons. It is this human-induced warming that is causing the ice caps to melt and the sea level to rise, a direct consequence of our industrial footprint on the delicate planetary system. But here is where a fascinating historical nuance emerges, a point that I confess astonished me when I first encountered it. Detailed records kept in the Antarctic ice core reveal that in the past, it was increasing temperatures that caused increasing CO2 levels. Imagine drilling deep into the ice, retrieving a cylindrical core that holds ancient bubbles of air trapped for hundreds of thousands of years. Analyzing these bubbles reveals the atmospheric composition of the distant past. And these records show that in previous natural warming cycles, the temperature rise often preceded the increase in carbon dioxide. Cause and effect were flipped, or at least the primary driver was different. But isn't that a blatant contradiction to what we understand about current warming? Well, actually, no. It's a testament to the intricate, interconnected dance of Earth's systems. Each positively influences the other, creating a feedback loop. It's just a case of which happens first. In the past, subtle orbital shifts, Milankovitch cycles, would cause a slight warming, which would then trigger natural processes that released CO2, like changes in ocean solubility or vegetation, further amplifying the warming. Today, however, our large-scale emission of CO2 from burning fossil fuels is the initial trigger, directly injecting vast amounts of heat-trapping gases into the atmosphere, which then causes temperatures to rise. We see this interplay, this powerful feedback mechanism, playing out vividly today as the increased temperatures of today's climate thaw the permafrost around the Arctic Circle. Imagine vast ancient lands frozen solid for millennia, now slowly softening like a giant thawing freezer. As this permafrost thaws, it begins releasing long-stored carbon reserves, vast quantities of organic matter that have been locked away in the ice for thousands of years. This released carbon, in the form of methane and carbon dioxide, in turn accelerates further global warming, creating a powerful feedback loop. It's a gentle reminder that Earth's systems are not static. They are dynamically intertwined, with each component influencing and being influenced by the others in a continuous complex dance. The mechanism by which increased CO2 and temperature affect the polar regions reveals a complicated and fascinating climate system, a subtle yet powerful ballet of energy transfer. Greenhouse gases trap infrared heat radiation emitted by the surface of the Earth. Imagine our planet as a warm body constantly radiating heat outwards, much like a cozy fireplace. These invisible gases in the atmosphere act like a thermal blanket, allowing sunlight to pass through to warm the surface, but then absorbing and re-emitting the outgoing heat radiation, preventing it from escaping directly into space. This heat is retained by the atmosphere and the ocean, and here's where the ocean's immense capacity truly shines. Around 90% of the energy increased is absorbed by the ocean, which is no surprise given it has almost 250 times the atmosphere's mass. Imagine two sponges, one tiny and one gargantuan. The colossal ocean sponge can absorb an immense amount of heat without its temperature rising dramatically, acting as a massive heat sink. This incredible thermal inertia of the ocean is a crucial moderator of our climate, buffering us from even more rapid temperature increases. So where does this extra energy go? Well, as anyone who's touched a hot stove or more unusually licked a ski lift chair on a cold day knows, heat always moves from hot things to cold things. It's a fundamental law of thermodynamics, a universal principle of energy transfer. And so it makes sense that it is at the cold poles where we see many times the average global temperature increase, because that's where the temperature gradient demands that the energy flows. It's like a warm current seeking out the coldest spot, gently but relentlessly transferring its warmth. And it's flowing there primarily through the ocean currents. Because of its density and heat capacity, water is very effective at transferring energy. Think of a warm bath. The water quickly envelops you in its heat. That's why water is used both as a coolant in cars efficiently carrying heat away from the engine, and a heating medium in homes gently radiating warmth through radiators. Conversely, air with a low density and low heat capacity is often used as an insulator. It doesn't hold much heat, and it doesn't transfer it well. That difference is profoundly evident in our everyday experience. That difference allows you to sit comfortably in a 90-degree sauna for many minutes, the hot air enveloping you in a dry heat, while you'd reflexively be unable to insert past your fingertip into water of the same temperature, which would instantly scald. The ocean's immense capacity to store and transport heat is a silent engine of global climate change, carrying the excess energy from the warmer parts of the planet towards the icy realms, gently, persistently melting them from within and from below. Tonight, our gentle voyage across the vast ocean of understanding brings us to the very edge of our planet's frozen heart. Last time we quietly contemplated the immense energy stored within ice and the intricate dance between atmospheric gases and ocean currents that drives its melting. Now let us draw closer to the ice itself to witness the delicate interplay of its various forms, sea ice shelves, and vast land sheets, and understand how the warming touch of the ocean is relentlessly reshaping the majestic yet vulnerable ice of our world. Imagine standing on a vast, shimmering plain of white where the air hums with a profound stillness. This is the West Antarctic Ice Shelf, a particularly vulnerable area, a colossal floating extension of the land-based ice sheet. It is a place of immense beauty and critical importance, a giant guardian that holds back even greater volumes of ice. This intricate region contains ice in several forms, each playing a distinct yet interconnected role in the grand planetary ballet of melt and freeze. To truly understand its fate, and by extension the fate of our coastlines, we must gently unpack these layers of ice, like turning the pages of a silent, frozen book. First, let us contemplate sea ice. This is the ice that forms directly on the surface of the ocean, a thin, shimmering skin that appears each winter and retreats each summer. It is very seasonal, a transient phenomenon responsible for the remarkable doubling of Antarctica's area through winter. Imagine the continent already vast, suddenly expanding its reach like a giant white cloak unfurling across the dark waters. This sea ice is born from the cold embrace of the polar night, freezing the ocean's surface into intricate patterns. And just as quickly as it forms, this ice melts through contact with the warmer ocean and the returning sunlight, much as ice cubes do in a cocktail dissolving quietly into the liquid from which they came. The direct impact of all the sea ice melting, if we were to consider it in isolation, would only contribute a few centimeters to sea level rise. This is because, like an ice cube already floating in a glass, the sea ice is already displacing its own volume of water. When it melts, that displaced water simply returns to its liquid form, causing minimal additional rise. However, its importance lies not in its volume, but in its profound role as a barrier to the otherwise exposed ice shelf. Think of it as a protective shield, a delicate yet crucial first line of defense for the colossal land-based ice. This protective sea ice performs several vital functions. It insulates the oceans from atmospheric warming, preventing the warmer air above from directly transferring its heat to the vast body of water below. It's like a colossal lid on a planetary pot, slowing down the simmering process. Furthermore, it keeps the humidity and temperature of the air above it low, creating a cold, dry microclimate that is essential for the continued stability of the polar regions. Being fresh and white, like the most fairy tale of glistening winter flurries, it also reflects a large portion of sunlight back into space. This albedo effect, the natural reflectivity of the bright white surface, is a powerful cooling mechanism, bouncing solar energy back into the cosmos before it can be absorbed by the darker ocean or land. But when this sea ice is low, when its protective shield shrinks or disappears, it exposes the ice shelf, that colossal floating extension of land ice that protrudes almost all the way around the Antarctic continent. Imagine the protective lid being lifted, exposing the precious contents beneath. These floating ice shelves can be truly gigantic, immense frozen platforms that dwarf human concepts of scale. Some, like the Ross and Rana-Filchner shelves, are greater in area than my home country, the United Kingdom, stretching for hundreds of thousands of square kilometers. They are magnificent silent sentinels, seemingly eternal, yet intricately vulnerable. And here, the story takes a more dramatic turn. The warm seawater eats at the underside of the shelves, relentlessly silently from below. Imagine a colossal frozen continent, gently but continuously, being eroded from its very foundations by an unseen force. This warming water, driven by subtle shifts in ocean currents, slowly thins the ice shelves, making them more fragile, more prone to fracturing. As it weakens, huge icebergs, the size of our biggest cities, can break away, tearing free from the main body with a roar that echoes across the frozen landscape, then drifting as far as Africa on the currents. These calving events are awe-inspiring spectacles, but they are also potent indicators of the increasing stress on the ice shelves. Since these ice shelves are melting, they also contribute minimally to the rising sea levels, much like the sea ice, as they are already floating. Their melting does not add new water volume to the ocean in the same way that land ice does. However, just like the sea ice, their importance lies not in their direct volumetric contribution, but in their critical silent role as a buttress. It's what the ice shelves hold back that has the most potential for sea level rise. They are the gatekeepers, the mighty dams that impede the flow of an even greater volume of ice that sits firmly on land and whose melt would directly contribute to rising sea levels. As the shelves shrink as their buttressing strength diminishes, the main body of sheet ice that sits atop land is more exposed. This exposure acts like a releasing of the brakes, allowing for faster flow rates from glaciers and ice streams. Imagine a colossal frozen river previously held back by a natural dam. When that dam weakens, the river's flow accelerates, rushing more swiftly towards the sea. These ice streams are not just small meandering rivers of ice. They are immense, silent behemoths, moving with an inexorable power. But don't be fooled. These ice streams are far bigger than their name would suggest. Incredibly, some are as wide as the mouth of the Amazon, stretching for dozens, even hundreds of kilometers across. They are hundreds of kilometers long and kilometers deep, profound, slow-moving rivers of solid ice, all flowing towards the sea, carrying immense volumes of frozen water from the heart of the continent. They are the arteries of the ice sheet, draining its vast reserves towards the ocean. And feeding these colossal streams is the colossal ice sheet itself, the vast continental-scale body of ice that covers Antarctica and Greenland. This is the ultimate reservoir, the true repository of Earth's frozen water. Since the ice sheet is supported on land, it behaves very differently from sea ice or floating ice shelves when it melts. Any mass of ice melt from this land-based sheet leads to a direct increase in sea level. It's like adding water to an already full bathtub. Every drop directly raises the waterline. This is the primary driver of future sea level rise, and it is here that the greatest potential for planetary transformation lies. It is important to acknowledge, however, that these ice melting processes are natural phenomena and would still occur without global warming. The poles are not static, unchanging monoliths. They are dynamic systems constantly gaining and losing mass. The poles take fresh snowfall and ice formation every year, which adds to the mass of the ice. This snowfall is like a replenishing rain, constantly adding new layers of ice to the ancient accumulation. And just for them to retain at their current size, we would witness sea ice melting, ice shelf calving, and glacial flow as part of their natural cycle of equilibrium. The ice sheets are constantly flowing, shedding ice at their edges and growing from fresh snow at their centers. This is the natural rhythmic breath of the ice. However, at this very moment, Earth's polar ice sheets are far from equilibrium. The delicate balance between accumulation and melt has been profoundly disrupted. The rate at which they are losing ice is quicker than fresh snow can fall, meaning that they are shrinking. It's like a bank account where withdrawals consistently outpace deposits. Eventually, the balance dwindles. Because of the extra energy in our oceans and in the atmosphere captured by greenhouse gases, we are already committed to significant ice sheet loss. Even if we were to miraculously halt all greenhouse gas emissions today, the warming already locked into the climate system would continue to melt ice for decades, even centuries into the future. It's a powerful testament to the long-term slow-moving inertia of Earth's vast climate machine. Can we say precisely how much sea levels will rise from this melting alone? This is where the intricacies of our planetary system truly come into play, offering a fascinating yet complex dance of interconnected forces. If you thought it would be a simple case of calculating the volume of ice lost and adding it to the volume of water in the seas, well, you can join me in being delightfully wrong. The reality is far more nuanced, far more intertwined with the subtle movements and responses of our dynamic planet. It's like trying to predict the exact path of a single raindrop in a complex storm system. There are many variables at play. To arrive at an accurate estimate, a true reflection of the future, we need to understand a few other interactions, subtle dances that happen beneath the surface of our awareness. We tend to think of Earth's crust as solid as an unyielding, rigid foundation. But given enough force, given enough time, the Earth will change shape too. It is not an entirely rigid sphere, but a somewhat pliable, elastic body constantly responding to the immense weights upon it. As the immense weight of the ice melts, the continental plate that supports it bears less weight and rises up above sea levels. Imagine a giant invisible hand lifting a colossal weight from a massive springy mattress. The mattress, now unburdened, slowly springs back up. This phenomenon, known as post-glacial rebound, is a slow, majestic process taking thousands of years to fully manifest. This rising of the land can, in some areas near the melting ice sheets, actually lead to a localized sea level fall as the land rises faster than the ocean. It's a surprising counterintuitive effect, a testament to Earth's dynamic responsiveness. But this rebound is not uniform. While the land near the poles might gently rise at the equator, the coastal land shrinks into the sea, creating localized sea level falls and rises. This is due to a complex gravitational effect. The immense mass of the ice sheets actually exerts a gravitational pull on the ocean, drawing water towards the poles. As the ice melts, this gravitational pull lessens, causing water to migrate away from the poles and towards the equator, contributing to sea level rise in those regions. It's a subtle dance of gravity and mass constantly reshaping the ocean's surface. However, the single biggest addition to sea level rise to date required no additional water at all. No melting ice, and was simply due to the thermal expansion of what was already there. Imagine heating a pot of water. The water itself doesn't just get hotter, it also expands, taking up slightly more space. Water, like most substances, becomes less dense as it warms, and our oceans, with their immense volume, have been absorbing the vast majority of the excess heat trapped by greenhouse gases. Around half of the sea level rise we have already seen since the Industrial Revolution has been due to this expansion. This means that even before significant ice melt began to contribute, the very water of our oceans, silently, invisibly, began to swell, pushing gently against the coastlines. This process is relatively easy to calculate, and we know how it will contribute to sea level rise in the future. It is a predictable consequence of a warming planet, a steady, gentle rise that adds to the more dramatic but less certain contributions from ice melt. However, the deluge of cold, fresh water being dumped into the salty sea has other, less predictable consequences, subtle ripples that can cascade through our planet's interconnected systems. Remember, Earth's systems are dynamically intertwined, like a vast, intricate clockwork where every gear influences every other. Adding fresh, cold water to the warm, salty ocean is like introducing a foreign element into a delicate chemical reaction. The outcome can be complex and surprising. It can affect ocean currents, marine ecosystems, and even atmospheric circulation patterns, creating a cascade of changes that are difficult to forecast with precision. A crucial feature of these dynamic systems is that they are vulnerable to dramatic changes in behavior known as tipping points. Imagine, if you will, playing a giant game of Jenga. The tower becomes less and less stable as we mine the lower levels for material to build even higher. Each block removed, each subtle shift, increases the precariousness of the structure. Eventually, merely touching the next brick, a seemingly innocuous action, brings it crashing down. This is the essence of a tipping point, a small perturbation that triggers a large, irreversible, and very rapid phase change in the system. It's a sudden, abrupt shift from one stable state to another, often with profound consequences that are difficult to predict or reverse. One such tipping point that could occur within our lifetime, a silent concern echoing from the depths of oceanographic research, is the slowing of the Atlantic Meridian Overturning Circulation, AMOCE. This is not just a passive current. It is an oceanic flow, a powerful energy transfer system, a vital artery of our planet's climate. Should it weaken or collapse completely, the consequences would be far-reaching and profoundly disruptive, altering weather patterns and sea levels across vast regions of the globe. It is a slow, colossal conveyor belt of water driven by a delicate balance of heat and salt, and its stability is crucial for the climate we know. Tonight, our gentle exploration takes us to the intricate heart of Earth's vast interconnected systems, where a delicate balance of heat and salt orchestrates a colossal dance. Last time we quietly contemplated the subtle yet profound ways melting ice influences sea levels and the concept of tipping points in our planet's grand climate system. Now let us delve into one such critical threshold, the Atlantic Meridian overturning circulation, or A&M Sumbaomi, a mighty oceanic conveyor belt whose gentle slowing could ripple across continents, reshaping climates and coastlines in unexpected ways. Imagine a colossal invisible river flowing deep within the ocean, spanning vast distances and carrying immense amounts of energy. This is the Atlantic Meridian overturning circulation, often simply called the AMOC. It is more than just a current. It is a powerful energy transfer system, an essential component of Earth's climate engine. Should it weaken or collapse completely, the consequences would be far-reaching and profoundly disruptive, altering weather patterns and sea levels across vast regions of the globe. It is like a silent underwater giant, gently persistently influencing the very air we breathe and the land we inhabit. The potential impacts of its weakening are stark and geographically diverse. Should this mighty current falter, sea levels on the eastern seaboard of America could rise by up to 1 meter. Imagine the already vulnerable coastal cities of the United States facing an additional meter of water, a silent, relentless encroachment that would exacerbate storm surges, intensify flooding, and put immense pressure on infrastructure and communities. It's a stark reminder of how far-reaching the consequences of such a subtle oceanic shift can be. But the effects are not uniform across the globe. In a curious twist in Europe, coastal waters would recede. This seemingly contradictory outcome is part of the complex dance of ocean dynamics, where water no longer being pulled by the AMOC's northern flow subtly shifts its distribution. However, this is little consolation, as Europe would face other, perhaps even more extreme consequences. The very fabric of its climate, accustomed to the AMOC's warm embrace, would be dramatically altered. Around the world, rainfall patterns would change drastically, pushing some ecosystems to become rainforests while pushing others towards desertification. It's a profound resculpting of global weather, a planetary domino effect triggered by a single colossal current. To understand how all of that is possible, let's look at how the AMOC functions. Now, the AMOC is not an isolated phenomenon. It is part of an even larger, more encompassing system known as the thermohaline circulation system. This grand oceanic conveyor belt is, as its name subtly suggests, driven by changes in heat thermo and salt concentration haline. Imagine a delicate balance, a precise recipe of temperature and salinity that dictates the water's density and thus its movement. Cold, salty water is denser and sinks, while warmer, less salty water is lighter and rises or flows on the surface. It's this continuous dance of density-driven currents that powers the AMOC. The AMOC acts as a vital circulatory system for the Atlantic Ocean. It brings warm tropical waters up past the United States and across to Europe, a colossal river of heat that transports warmth from the sun-drenched equator to the cooler northern latitudes. This vast transport of warmth is a critical reason why northern Europe is warmer than it ought to be, considering its proximity to the polar circle. Imagine cities like London or Paris, far north on the globe, enjoying temperate climates. This is in part a gift from the AMOC, a warm embrace from the tropics that keeps the chill at bay. Without this warm current, Europe's climate would be drastically colder, perhaps more akin to parts of Canada or Siberia at similar latitudes, as these warm waters continue north to the Arctic. something crucial happens. They gradually cool, and crucially, as they encounter colder air, some of the water freezes into sea ice. When seawater freezes, the salt is largely excluded from the ice crystals, leaving the surrounding unfrozen water even saltier and thus denser. This process leaves cooler, saltier water to sink to the bottom of the ocean, where it then flows back south to complete the cycle. This sinking of dense, cold, salty water in the North Atlantic is the engine that drives the entire AMOC. It's like a perpetual motion machine powered by the subtle interplay of freezing and density. However, a new and powerful force has begun to disrupt this delicate balance. The melting of the Greenland ice sheet is inundating the northern part of the AMOC with fresh water. Imagine a colossal freshwater faucet, gently yet persistently pouring vast quantities of relatively light, unsalty water into the region where the AMOC's engine is supposed to be working hardest. This influx of fresh water dilutes the seawater, making it less salty and less dense. And herein lies the problem. If the water is less salty and therefore less dense, it has less propensity to sink. This makes the gradient directing the water to sink to become shallower, slowing down this part of the cycle and reducing flow. Imagine a very heavy object sinking quickly in water. If you make it lighter, it will sink more slowly or not at all. The very buoyancy that drives the deep water formation is being subtly undermined by the freshwater influx. It's like a slow middle lane driver on the motorway can cause a tailback stretching frustratingly far back across all lanes. The slowing down of the AMOC backs up water on the American East Coast, leading to higher sea levels there, and simultaneously reduces the flow of warm water to Europe, meaning that sea levels would rise in America, while Europe would be spared the direct sea level rise. Though that's little consolation to a continent that will lose much of its way of life and food production capacity through cooler temperatures. The warming touch of the AMOC has made European agriculture and daily life possible in its current form for centuries. The United Kingdom alone is facing an average temperature drop of 10 degrees Celsius, which would make it colder than Iceland. Imagine the profound societal and environmental transformations. Such a sudden drop in temperature would bring altered growing seasons, increased energy demands for heating, and a complete re-evaluation of long-established cultural norms. It's a stark example of how interconnected our climate systems are, and how a seemingly distant oceanic shift can have profoundly personal consequences. Now, as we contemplate the melting of these ancient ice sheets, another more subtle and perhaps unsettling layer of mystery begins to emerge. The melting Greenland ice sheet also contains organisms that we haven't seen on Earth in hundreds of thousands of years. Imagine a vast frozen time capsule slowly thawing, releasing dormant life forms back into our modern ecosystems. These aren't necessarily monstrous creatures, but microscopic entities, ancient bacteria, viruses, or spores that have been preserved in suspended animation within the ice for eons. When a new predator travels to an ecosystem not evolved to live with it, it can upset its delicate balance. This is also true of a pathogen traveling through time. Our modern ecosystems, our plants, animals, and even our own immune systems have evolved in response to the pathogens of our current era. Introducing ancient long-dormant microbes could be profoundly disruptive. Most of these species will likely be harmless, just ancient passengers, harmlessly stirring a wake. But as we saw in 2020, with the unexpected arrival of a global pandemic, it only takes one black swan to change everything. A single highly transmissible or particularly virulent ancient pathogen for which our modern world has no immunity or defense could have devastating consequences. With more cells being released from ice melt each year than there are grains of sand on Earth, the sheer volume of biological material being reintroduced into the environment is staggering. The risk that one is a black swan event, a completely unexpected and highly impactful pathogen, is significant. A risk that increases with a depth with the permafrost thaw. The deeper the ice and permafrost, the older the trapped organisms And the further back in time a potential pathogen is, from the bigger the jump in its genome and the lower our ecosystem's readiness for it. It is a quiet yet profound concern, a potential hidden danger lurking within the very ice that is melting around us. So the world is changing subtly and dramatically, right beneath our feet and around us. As we have seen, ice is an incredible recorder of Earth's history. It is a silent, meticulous archivist, preserving layers of snow year after year, trapping bubbles of ancient air dust from distant volcanoes and even microscopic life forms. Through studying its secrets, through careful analysis of ice cores, we can see Earth's past. We can glimpse ancient climates, atmospheric compositions, and even the subtle fingerprints of past geological events, just as the ice cores detail Earth's ecosystem, as the Bering Strait flooded, allowing ancient land bridges to appear and disappear. They also contain our history too. They hold records of our industrial past, of the gases we've emitted and the chemicals we've produced. And as the ice melts, it replays our environmental missteps by re-releasing trapped chemicals we have produced. This is a profound and sobering thought. The very ice we melt is not just water, but a time capsule of our own past environmental actions, now returning to haunt us. Consider the chemicals now long dormant that could be reawakened. CFC's chlorofluorocarbons, for example, once widely used in refrigerants and aerosols, were banned decades ago due to their devastating effect on the ozone layer. Yet those stored in the ice can again deplete the ozone as they are released, accelerating Arctic ice loss in a vicious feedback loop. Similarly, chlorinated pesticides, many long banned from use due to their toxicity and persistence, can find their way back into Earth's ecosystem, contaminating soil and water. Some of these may have been made even more potent by their time stored in ice, their chemical structure subtly altered by the unique conditions of preservation. And then there's the silent legacy of early industrialization. Vaporized lead from the use of leaded petrol, once a ubiquitous pollutant, will also be re-released as the ice layers that contain it melt away. This chemical cocktail adds yet more stress to a global ecosystem, moving ever closer to an invisible edge. It's like adding tiny invisible burdens to an already straining system, each one pushing it closer to a tipping point, a threshold beyond which the changes could become far more dramatic and irreversible. This release of ancient pollutants is a silent, creeping consequence of our past actions, now returning to influence our present and future. When we add all these factors together, the direct ice melt the thermal expansion of the oceans, the potential weakening of great ocean currents like the AMOC, and the release of ancient pathogens and pollutants, the year 2100 could look very different. It is not a fixed point, but a range of possibilities, a spectrum of futures that depend on the choices we make today. The current predicted average sea level rise is 0.5 meters. That doesn't sound like much, does it? Half a meter across the vastness of the ocean might seem negligible to the casual observer. A map of the world's coastlines would look almost unchanged to the naked eye, perhaps just a subtle blurring of the edges. However, the true impact is not in the averages, but in the black swan events, the storms, the floods, the heat waves that drive human behavior. A seemingly small average rise can dramatically increase the frequency and intensity of extreme weather events, making coastal communities far more vulnerable. A storm surge on top of a higher baseline sea level means greater inundation, more damage, and more displacement. By the year 2100, a population the size of the U.S. will be exposed to regular coastal floods. Imagine an entire nation, its cities and towns along the coasts, facing the constant threat of inundation, not as rare disasters, but as recurring, predictable events. Faced with increased risk, where will Earth's coastal populations move to? What will be the societal cost? The human displacement, the cultural loss of leaving ancestral homes. How much will our way of life change? These are profound questions that extend beyond mere scientific prediction into the realm of human adaptation and resilience. Yet amidst these significant challenges, there is a deep well of hope. The rich diversity we see in cultures and species on Earth is born out of adapting to the environment. Our planet is a testament to the power of adaptation of life, finding a way no matter the obstacle. Both humanity and life itself have demonstrated time and time again that they are irrepressibly adaptive. We are problem solvers, innovators, capable of immense change when faced with adversity. Humanity can and has to learn from its past and look to the future. The lessons from ancient cultures that adapted to changing climates from our own species' ability to innovate and overcome challenges offer a powerful narrative of resilience. So, there is hope. While the melting ice reminds us of the environmental damage we have been responsible for since the Industrial Revolution, it also reminds us of how often we came together to make a change for the better when we understood how we were affecting our planet and ourselves. Think of the successful efforts to address the ozone layer depletion, a global problem that was tackled through international cooperation and decisive action. I believe we can and need to do it again. The challenges are immense, the stakes are high, but the capacity for human ingenuity and collective action is equally profound. It is a call to gentle yet determined action, to look honestly at the future, and to embrace the responsibility we hold for the delicate balance of our planet. And as we conclude this chapter, let us hold on to that hope, that quiet belief in our collective ability to navigate the currents of change and to forge a more sustainable future for the generations to come. For the Earth whispers not just warnings, but also quiet inspirations, urging us to listen and to act with wisdom and foresight. Tonight we arrive at the final chapter of our gentle journey, a quiet culmination of the intertwined stories of deep oceans, distant space, and the mighty forces that shape our planet. We've drifted through ancient ice, pondered the profound implications of its melt, and glimpsed the delicate balance of Earth's vast climate systems. Now, as our thoughts settle, let us look to a different invisible force that graces our poles, a recently confirmed energy field that speaks to the very habitability of our world and others. And finally, we will journey to a familiar yet alien world, Mars, to discover its subtle whispers in the sand, a fitting conclusion to our exploration of surprising connections. Above our planet's poles, an invisible force is at work, a silent sculptor of our atmosphere. This force, though hypothesized decades before we were able to measure it directly, has now revealed its subtle yet profound presence. This global energy force is responsible for sculpting our atmosphere and driving charged particles into space. It is, in a very real sense, a cosmic breath exhaling tiny fragments of our world into the void. It's also why some planets end up uninhabitable, altogether stripped bare of their precious atmospheric cloaks. This subtle yet powerful influence is called the ambipolar field, and it's a force as fundamental to our Earth as gravity or magnetic fields. Imagine a delicate, shimmering veil, almost imperceptible, yet profoundly influential in the grand ballet of planetary existence. Although for the sake of life on Earth, it's a good thing it isn't too strong. A stronger field, as we will gently discover, can have devastating consequences for a planet's ability to retain the very ingredients for life. The universe, in its wisdom, has found a delicate balance for our world. And it is through recent breakthroughs from NASA's Endurance mission that scientists have finally been allowed to solve a 60-year-old mystery by measuring the ambipolar field for the first time, proving once and for all that our planet has a third global energy field. This was not a sudden dramatic explosion of discovery, but a quiet, patient accumulation of knowledge, culminating in a precise measurement that confirmed a long-held theory. I'm Alex McCohen, and you're watching Astrom. Join me today as we unravel the mystery of our planet's ambipolar electric field, a phenomenon that not only powers the polar wind, that gentle escape of our atmosphere, but also has an enormous impact on our planet's habitability, a silent guardian of our watery world. To fully appreciate the ambipolar field, let's briefly reflect on the familiar forces that already cradle our world. Earth's magnetic field, often depicted in this video as onion-like layers of lines, like invisible force fields swirling around us, helps to shield our atmosphere from dangerous solar energy and damaging cosmic rays. Imagine it as a giant protective bubble, deflecting the harsh winds from the sun and the powerful radiation from deep space. Without it, our atmosphere would be stripped away, leaving our planet barren and exposed. And the gravitational field shown here as the white glow around our planet is perhaps the most familiar of all. It not only keeps us planted on Earth's surface and stops our atmosphere from drifting away, a constant, gentle pull that grounds us in reality, but also provides valuable information in the study of Earth's changing climate, sea level rise, ocean circulation, and much more. It is the fundamental anchor, the invisible hand that shapes landscapes and dictates the very flow of our oceans. As you can see, our magnetic and gravity fields are critical features that help make our planet habitable, creating the delicate conditions for life to flourish. And with the recent publication of a 2024 paper in the journal, Nature Direct evidence has finally been found for a third energy field, the ambipolar field. This discovery adds another layer to our understanding of Earth's intricate planetary ballet, revealing a subtle yet profound force previously beyond our grasp. To truly understand this new layer, this silent influence, we need to talk about plasma. Like a solid liquid or gas, plasma is another state of matter often called the fourth state. It happens to make up 99% of all visible matter in the universe. Imagine the stars, the nebulae, the very sun that warms our day, all are made of plasma. Plasma is essentially gas that has become ionized, meaning its atoms have been stripped of some of their electrons, leaving behind a swirling soup of charged particles. It is responsible for several well-known phenomena on Earth, like the mesmerizing aurora borealis, the dancing northern lights that paint the polar skies, and the dramatic crackle of lightning during a storm. Plasma can form where atmospheric gas density becomes low enough to support the conditions for it, and around 90 kilometers above Earth's surface, in the upper reaches of our atmosphere, this plasma begins to emerge. This specific plasma is made up of very lightweight, fast-moving particles, which get trapped along the Earth's magnetic field lines as they move away from the surface. Imagine tiny charged dancers caught in the invisible magnetic currents swirling upwards, drawn by an unseen force. Around the majority of our planet, this plasma encounters a barrier that limits its escape into space, known as the plasmasphere. Here, plasma co-rotates along with Earth, along its closed magnetic field lines, a graceful contained swirl locked in Earth's gravitational and magnetic embrace. Until the mid-1960s, the prevailing model of our planet's magnetic field theorized that all of the magnetic field lines were closed, like invisible loops connecting the north and south poles, and the plasma remained trapped within this magnetic cage. So what changed? We went to space. The advent of space exploration. The ability to send instruments beyond the confines of our atmosphere opened a new window onto our planetary neighborhood. In the 1960s, the first spacecraft flying over our planet's north and south poles could actually detect a supersonic wind of charged particles or plasma flowing out to space, a gentle but steady stream of our atmosphere escaping into the vast void. This escape included positively charged hydrogen and oxygen ions, the very building blocks of water and air. This unexpected observation led scientists to start wondering whether the Earth's magnetic field model should have an open rather than a closed tail, suggesting that some magnetic field lines, especially at the poles, might stretch out into space, acting as conduits for this escaping plasma. At the time, scientists already knew that our atmosphere lost some particles to space due to thermal escape. This is a type of atmospheric escape that typically happens when the energy from sunlight heats up particles in our atmosphere, allowing them to reach escape velocity and break free of our planet's gravitational pull. It's kind of like when a pot of water boils and steam evaporates. The heated water molecules gain enough energy to leave the liquid surface. So, it was no surprise that some particles would be escaping into space through this thermal process. But something didn't quite add up. If energy from the sun were the only cause of atmospheric escape, one would expect the particles that were escaping into space to be heated, their energy levels visibly elevated. However, many in the stream were actually cold, remarkably so with no signs of being heated, and yet they were traveling at supersonic speeds, a paradox that defied simple explanation. How could cold particles gain such incredible velocity? Scientists hypothesized that there must be another invisible force driving this phenomenon, a subtle but powerful push that didn't rely on thermal energy. And in 1968, the term polar wind was coined to describe it, leading to more research and theories into its cause, and effects a quiet revolution in our understanding of planetary atmospheres. The idea of a planet-wide electric field was then developed to explain the polar wind, a subtle electrical potential gently nudging these cold particles outwards. But when this was theorized in the 1960s, it was thought that the force was too weak to detect, and at the time, scientists were correct. The electric potential was so weak, it would require very sensitive instruments to measure, and that technology wouldn't be invented for several more decades. It was a beautiful hypothesis, waiting patiently for technology to catch up, like a seed waiting for the right conditions to sprout. Enthusiasm to measure our planet's ambipolar field was spurred again in 2016 after a clue came from the European Space Agency's Venus Express mission. This distant planetary neighbor held a vital piece of the puzzle. One of the primary reasons that Earth is hospitable for life is because of its abundant water, a shimmering blue jewel in the cosmos. While Venus today is dry and barren, a scorching, inhospitable world, billions of years ago, evidence suggests that Venus might have had abundant water like our own world does now. This raises the intriguing question: if Venus once had water, where did it all go? What cosmic process robbed our sister planet of its life-giving liquid? The ESA's Venus Express mission offered a potential explanation when it detected a 10-volt electric potential around Venus, an electric field at least 5 times larger than expected. This marked the first successful measurement of an electric field on any planet, including Earth. The electric field surrounding Venus could pull positively charged ions like oxygen out of the atmosphere, effectively draining it of the essential ingredients of water, like a powerful vacuum cleaner, siphoning particles out to space. Over time, this could have played a crucial role in draining the planet of its once abundant water, transforming it from a potentially habitable world into the desolate furnace we see today. It was a profound insight into planetary evolution, a warning whispered from a neighboring world. This compelling discovery on Venus prompted a question much closer to home. Does Earth have a similar electric field? And if so, why has our planet managed to hold on to its water? The electric potential measured around Venus was around 10 volts. For comparison, a standard car battery is 12 volts, a familiar measure of electrical power. But scientists expected our planet's electric potential to be as little as 0.3 volts, similar to a button battery you might find in a watch, and some 25 times weaker than the electric potential on Venus. It's this seemingly small difference that may be a key reason why our Earth has been able to keep its water, a subtle yet critical distinction that has allowed life to flourish. And that's what inspired NASA's Endurance team to develop a new type of scientific instrument called a photoelectron spectrometer to find Earth's weak electric field, a delicate sensor designed to perceive the almost imperceptible. Earlier, I explained thermal escape, and I mentioned that particles are able to escape from our atmosphere when they reach escape velocity. That escape velocity is a very specific, predictable speed the velocity an object needs to break free from a planet's gravitational pull. But this speed should be ever so slightly slowed by Earth's electric potential, a subtle braking effect, like a gentle, invisible hand. And so by measuring that slowing effect at apogee, or the furthest point in Endurance's orbit from Earth, the instrument would be able to measure the strength of the electric potential around our planet. It was an ingenious method using the most minute changes to reveal a vast, unseen force. Such a sensitive instrument would need to be launched at precisely the right location and time where the electric field's effects would be most pronounced and least obscured by other atmospheric phenomena. In order to ensure a chance at making the observation successful, the Svalbard rocket range was selected for the job. It's the northernmost range in the world, located in Svalbard, Norway, a remote group of islands nestled in the Arctic Ocean. Here, the NASA Endurance team would be able to launch the instrument on a suborbital rocket through Earth's magnetic North Pole, a strategic vantage point where the magnetic field lines are open, allowing the polar wind to flow freely. And on the 11th of May 2022, the dedicated team of international scientists did just that. Named after the ship that carried Ernest Shackleton's crew in their 1914 attempt to reach the South Pole and cross Antarctica, a name that evokes resilience and profound journeys into the unknown. The Endurance mission launched its suborbital rocket to an altitude of 768 kilometers, collecting data over 518 of those kilometers before splashing down 19 minutes later in the Greenland Sea. It was a brief but intensely focused mission, a precise dart into the upper reaches of our atmosphere, seeking a whisper of an answer. During its fleeting flight, the instrument measured a change of 0.55 volts in electric potential between 250 kilometers and 768 kilometers. Space scientist Glenn Collinson, the principal investigator for NASA's Endurance mission, humbly yet triumphantly stated that even though half a volt is almost nothing again, almost about the strength of a watch battery, it's just the right amount to explain Earth's polar wind. This first ever direct measurement of Earth's electric field marked a pivotal moment in our understanding of this fundamental planet-wide energy force, confirming decades of theory with concrete data. It was like finally hearing the quiet hum of a distant machine confirming its existence. The ambipolar field exists in what's called the ionosphere, a vast region that stretches across 3 out of 5 of our atmospheric layers. Our atmosphere, that protective blanket that cradles our planet, is divided into 5 main layers, each with its own characteristics and hidden wonders. The troposphere, also known as the lower atmosphere, only reaches about 20 kilometers above Earth's surface and is where the majority of weather occurs, where clouds gather and storms brew. Next is the stratosphere, which extends up to about 50 kilometers and contains most of our planet's ozone that protects us from ultraviolet radiation from the sun, a vital shield against harmful cosmic energy. This layer has very little circulation and is where commercial airlines usually fly, gliding smoothly above the weather. Above the stratosphere is the mesosphere, extending up to about 85 kilometers. This is where meteors burn up near the bottom of the mesosphere layer, their friction with the increasingly thick air, causing them to glow and disintegrate, protecting us from celestial debris. It's within the upper reaches of the mesosphere that the ionosphere begins, but its influence stretches far beyond that. Starting around 80 kilometers above the surface in the mesosphere, the ionosphere continues outward through the entire thermosphere layer from about 85 to 600 kilometers. This is where auroras happen, where high-energy ultraviolet and X-ray radiation are absorbed, creating charged particles that dance in the polar night. And finally, the ionosphere ends in the lower exosphere, which begins around 600 kilometers and continues out to about 10,000 kilometers from Earth's surface, where it fades into outer space, gently merging with the cosmic void. The exosphere is where many satellites orbit around our planet, silent guardians in the high frontier. As you can see, the ionosphere starts around 80 kilometers above sea level and stretches hundreds of kilometers into space, where it overlaps with Earth's magnetosphere, a region of space surrounding Earth like a vast invisible cocoon. Within this massive region of the ionosphere is where we find the ambipolar field, which is theorized to begin at around 250 kilometers. While most of our atmosphere is composed of nitrogen, a relatively inert gas, the upper region of our ionosphere is home to lighter elements like oxygen, hydrogen, and helium. When photons from the sun collide with these elements in the upper atmosphere, they can knock electrons loose from the elements in a process called ionization, creating positively charged particles, called ions, and negatively charged electrons. Imagine a cosmic billiards game where sunlight's energy is the cue ball striking atoms and dislodging their electrons. Because of the opposite charges of the negative electrons and positive ions, they are attracted to each other and become tethered together by an electric field, a subtle, invisible bond. It's this electric field that constitutes a major part of the ambipolar field, an intricate dance of attraction and repulsion. The electrons within the electric field are so light that the slightest push could send them flying out to space their minuscule mass, making them highly susceptible to electric forces. While the ions are more than 1/800 times heavier than the electrons and sink toward the ground due to gravity, a constant, familiar pull. The subatomic tug of war works in both directions, a delicate balance of opposing forces, but the upward tug from the energized electrons is able to just slightly overwhelm the force of gravity on the ions. This outward pressure of ionospheric electrons is what creates the ambipolar field depicted here as the sparkling blue glow around our planet. This gentle upward push inflates our planet's ionosphere, stretching it outwards, and accelerates some ions enough to escape from the atmosphere, creating the polar wind along our poles. Magnetic field lines a continuous subtle exhale of our world into the cosmos. What's more, the ambipolar fields can achieve this acceleration of plasmas without heating them, providing a beautiful and elegant explanation for the cold plasma scientists have detected escaping from the ionosphere, solving a long-standing mystery. It's the bidirectional nature of the interaction between ions and electrons that gives the ambipolar field its name. The Latin prefix ambi means both, referring to the dual forces, and polar refers to the polar regions where the electric field's effects are felt the strongest, where the magnetic field lines open up into space. Collinson, the Endurance mission's primary investigator, aptly called the ambipolar field an agent of chaos, subtly stripping particles from our atmosphere away into space. Hydrogen ions make up the majority of the polar wind. They are so light that the ambipolar field's upward force on these electron ions is 10.6 times stronger than the force of gravity, leading the ions to accelerate up at supersonic speeds and escape from our atmosphere above the Earth's magnetic poles. It's a silent, relentless outflow, a gradual thinning of our atmospheric veil. Scientists have found that our planet loses about 3 kilograms of hydrogen gas every second, or 95,000 tons per year, a steady continuous bleed into the vacuum. Additionally, the Earth also loses about 50 grams of helium per second, or 600 tons of helium gas per year, a smaller but still measurable amount, and a much smaller amount of other gases like oxygen. However, not all of this atmospheric loss is due solely to polar winds. It occurs through a combination of factors, including thermal escape, the gentle boiling off of heated particles, and other non-thermal escape mechanisms such as the polar wind. But don't worry, despite our planet losing several thousand tons of its atmosphere to space every day, we are nowhere near running out of air. The planet won't run out of oxygen for 1 billion years. It will be another 1 billion years after that before our oceans will have been depleted of most of their hydrogen. Around 4 billion years from now, our planet may look very similar to how Venus looks now, a scorching, barren world. All of our water will have evaporated, and the greenhouse effect will have become strong enough to melt rock, leaving our planet a dry, lifeless world. Keep in mind that modern humans have only existed on this planet for around 300,000 years. Our species would need to exist more than 3,300 times that length to be around in 1 billion years. While not really important on human timescales, it is still interesting to think about, though, a silent testament to the vastness of cosmic time. And while hydrogen ions may be the lightest and most common type of ion to escape in a polar wind, heavier particles also get a boost from the ambipolar electric field, helping to shape our atmosphere's structure and dynamics in subtle yet profound ways. How exactly? Well, now that we've measured the ambipolar field, scientists can delve into all the ways the ambipolar field shapes our atmosphere. Take oxygen ions, for example. These heavy ions weigh half as much when they're immersed in the 0.55 volt ambipolar field. This effect increases the ionosphere's scale height by 271%, which means our atmosphere can remain denser at greater heights than it would otherwise be able to. Endurance's discovery and measurement of the ambipolar field also provided an important key to understanding why Earth has been able to hold on to much of its water up until this point, while our neighboring planet Venus was not able to do the same. It's theorized that any planet with an atmosphere may also have an electric field, and you may recall that earlier I said Venus's electric potential was measured to be around 10 volts, roughly 18 times stronger than the ambipolar field on our own planet. While Earth does lose a constant flow of particles to space, both through the polar wind as well as other types of atmospheric escape, this effect would have likely been much more pronounced on Venus because of its stronger electric potential, leading to the loss of heavier particles like the ones that make up water. The fact that our ambipolar field is so weak may be an important part of why our planet has been able to hold on to its water, a delicate balance that has allowed life to flourish for billions of years. We've only just started to explore the depths of how the ambipolar field has influenced our planet and life on Earth. And the Endurance scientists have said there are already plans for additional measurements of our planet's ambipolar field in the future. Like its predecessor, the new rocket will also carry the legacy of a long-past Arctic explorer. Named after the Resolute, a ship that set off to explore the Arctic in 1850. And now that we've finally been able to confirm and measure the ambipolar field strength, and with a follow-up mission already planned to take more measurements, scientists can start asking some of the bigger and more exciting questions, like what it means for Earth's complex atmospheric dynamics and how it helps to govern planetary evolution. And doesn't the potential insights we stand to gain from this research feel electric? As we gently transition to our final realm of exploration for tonight, let us turn our gaze to a world that feels both familiar and deeply alien: Mars. NASA's Mars Reconnaissance Orbiter has been imaging the surface of Mars for over 10 years now with its powerful, high-resolution imaging science experiment, or HiRISE camera. 10 years of taking photos every day means that its catalog is huge, and we can pick out pretty much any part of Mars that we want to have a closer look at. Tonight, I thought it would be really interesting to investigate the sand dunes on Mars and see how they compare to the wonderful sand dunes we have on Earth, those gentle waves of solidified wind that grace our deserts. You may have already seen imagery of the Sahara Desert, with dunes hundreds of meters tall, like sleeping giants stretching across the landscape, or the Namib Desert, with rolling sand dunes as far as the eye can see, a vast undulating sea of sand. Did you know, though, that there are 5 different types of sand dunes, and that Mars has a type of dune Earth doesn't have? And also, what are the biggest dunes on Mars? The most common type of sand dune on Earth is the crescent, or the Barshan sand dune. While not always as distinctive as these dunes in this image, with their perfect crescent shapes, they are plentiful and found in most sand deserts. They are defined by this kind of crescent shape with arms that point downwind, and they are usually wider than they are long. Like you can see here, like a collection of gentle wind-sculpted smiles. They form like this because in these places there is only one dominant wind direction pushing the sand consistently in a single path. They have a shallow slope on one side that faces the wind where the sand is gently pushed up, and a slip face on the other side, a steeper slope where the sand tumbles down. They are a type of transverse dune forming perpendicular to the wind direction. As they move gradually over time, as the wind blows whipping sand from the front over the top and down the slip face, they slowly migrate across the landscape, leaving their ephemeral traces. When many of them merge, they can create an almost wave of sand smooth on the side, facing the wind with a slip face away from the wind, moving gradually over time with the wind's direction. They are also in plentiful supply on Mars, a familiar echo on a distant world. All of the ones I'm about to show you can be found at the base of various large craters where sand collects and the winds swirl. Going to this old crater near Mars's equator, Barchan dunes can be seen lumped together somewhat here in this plain, like scattered frozen puddles of sand. This happens when there is a plentiful amount of sand and the dunes merge together into a big lumpy transverse dune, a complex interconnected system of sandy waves. But individual dunes are really evident a bit higher up, where the sand is contrasted against the bedrock standing out like dark jewels against a lighter canvas. Here are some more found in Archangel Ski Crater, beautifully isolated formations. When there is a smaller amount of sand, the dunes tend to stay separate, which looks really peculiar from above, like scattered teardrops on the Martian surface. These dunes do move, although very slowly. Here's a couple of examples of dunes on Mars moving slowly over the course of 2 to 3 years. Scientists originally thought that sand dunes would stay pretty motionless on Mars, as sand dunes require wind to move them, and Mars only has about 1% of the atmospheric pressure at the surface, compared to Earth, whose winds can easily move sand. The Martian atmosphere, thin and wispy, seemed too weak to sculpt such grand forms. We knew the wind on Mars could pick up tiny dust particles, creating vast planet-enveloping dust storms, but it would require extremely strong winds to move sand, which is heavier. This could be helped, though, by the fact that sand on Mars is not exactly the same as Earth's sand. In my Opportunity video, I mentioned that the sand particles Opportunity analyzed were far smaller than what we're used to on Earth, which may aid the movement of these dunes, allowing them to dance to the tune of even a gentle Martian breeze. But what happens if the wind is bidirectional, shifting its direction over time? Going back to Earth, a beautiful type of dune, which can easily be seen all the way from the International Space Station, is the longitudinal, or SEF, an Arabic word for sword dune, which describes these dunes nicely, as they are long and narrow, like elongated sandy blades stretching across the landscape. These linear dunes can be hundreds of kilometers long and are often found in parallel sets, separated by gravel or rocky corridors, creating a vast striped pattern on the desert floor. These occur where wind directions can flip over, meaning that these ridges have a slip face on either side of the dune, making them appear quite sharp like a perfectly honed blade. Safe dunes also appear on Mars, a further testament to the shared geological processes across planets, and in my opinion, the most beautiful example of it can be found here, again found at the bottom of a crater, a natural amphitheater for these sandy sculptures. These dunes look remarkably similar to each other, including this dusty band found on each one, a subtle pattern of layered material. Although we're not totally sure how they form one, leading theory is that they are the result of wind directions changing around Barchan dunes, gradually stretching and elongating them into these linear forms. In this image, some Barchan dunes seem to be mid-process of forming into Sif dunes, a quiet ongoing transformation. It's a really pretty image that seemingly tells a story of wind and sand, a narrative etched onto the Martian surface. To our right here, we have a mesa being eroded, feeding sand into the valley below, a constant supply for the wind's artistry. Then you have these beautiful examples of Barchan dunes, which show the step-by-step process of becoming CEF dunes. Another spectacular example of this, a bit further into the process, can be found here. The contrasts of the different materials in the image are stunning, and the dark sections are the sand dunes merging together, forming a complex evolving tapestry. The third type of dune is the dome dune. Typically, these are not very big on Earth, usually only a few feet high. They have no slip face. They are smooth all over, hence the name, like gentle rounded mounds. They are quite rare and usually found in and around other types of dunes, as if they are the quiet, unassuming neighbors in a bustling sandy community. And yes, These are also found on Mars, though, with a distinct Martian flavor. Here's a field full of domes, a few of which can be seen starting to cross over into Barchan dunes, hinting at a transitional phase. And in this impressive expanse of dunes, and I really do mean an expanse, as these dunes continue on way beyond this image, you have wobbly lines of dunes with domes on the end of them, like a meandering river of sand. These domes seem to be much bigger here than they are on Earth. The domes here, tens of meters across, colossal in comparison. This field is indicative of a change in wind direction, as the lines are nowhere near as straight as in some of these previous images, suggesting a more complex multi-directional wind pattern that shapes these unique formations. The fourth type of dune is a parabolic dune, which is the opposite of a Barchan dune, meaning the slip face is on the other side, compared to a Barchan dune with its arms pointing upwind. These occur near coastal regions or areas with some vegetation, and form the way they do because something off in vegetation anchors the arms of the dune in place, preventing them from migrating downwind. The lack of vegetation on Mars means it's a bit tricky to find parabolic dunes in their classic form. The closest thing I found is this beautiful image, a dune wrapped around a large mound in the middle, almost embracing it. The dune is clearly moving from left to right in this image, a slow geological migration. And you can even see the shadow of the slip face just by here on this side, cast by the low angle of the sun. The existence of this dune is heavily influenced by the size and shape of this mound-funneling wind along its walls, creating a localized environment for its formation. The fifth and last type of dune is the biggest type, the star dune. This is a dune where wind direction changes frequently, coming from multiple directions, meaning the dunes in this region have 3 or more arms and are often stationary, just building up over time, growing taller and more complex as sand is deposited from all sides. This impressive image is the Sahara Desert as seen from the ISS, and it is full of star dunes like colossal 3-dimensional stars scattered across the vast sandy expanse. The scale of these dunes truly is impressive. Zooming in, you'll realize that these dots are people minuscule against the grandeur of these sandy mountains. And of course, we have star dunes on Mars. Some are small, a collection of dunes merged together, but others are massive, like these found in Russell Crater, which reach far beyond this image, towering monuments of sand. As this image is found nearer the poles, carbon dioxide ice can form on these dunes, a shimmering layer of frozen gas. During the Martian spring, the carbon dioxide sublimates, turning directly from solid to gas, which dislodges loose material, leaving these streaks like ephemeral fingerprints on the sandy surface. Moving to another image again near Mars's pole, we find one of the most beautiful images of Mars I have ever seen. This image was taken just as the sun was either rising or setting, meaning a lot of the image is shadows cast by dunes stretching long and dramatic across the landscape. I love this as it provides a sense of depth to the image, transforming a flat photograph into a 3-dimensional world. These again are big star dunes with their individual arms reaching out for kilometers, silent, sandy giants sculpted by the Martian winds. There's one last thing I want to talk about the dunes of Mars, a subtle detail that speaks volumes about the planet's hidden secrets. Have you ever been to the beach and seen sand ripples like these? These are actually a type of transverse dune forming perpendicular to the direction of the water waves as they flow over the sand, much like larger-scale transverse dunes caused by the wind. They are tiny, intricate patterns, a microcosm of the grander forces at play. Mars has these ripples too, but they are much, much bigger than what you would find on Earth, with a meter or two between the ripples, like colossal frozen waves. This size makes it difficult to see from space, but luckily, we have another rover on hand, Curiosity, seen here in this image, to take this remarkable photo of them. Scientists didn't even know this type of dune existed before Curiosity saw them up close. And it is a fitting reminder that although Mars may appear quite familiar to us with its craters and canyons and sand dunes, it is still a world full of secrets and unexplored facts. And there is still so much we can learn from it, just as there is from the hidden depths of our own ocean. Making this video required some long-term planning and work, which we were only able to do thanks to the consistency and sustainability of your memberships as astronauts on Patreon. A huge thank you to everyone who has signed up. And if you'd like us to make more videos like this, you can join with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.